Hi.
Anu? Start ചെയ്തോ.
Good evening to one and all. I welcome our Honorable Registrar, Professor R. Thirumurugan, our beloved faculties, resource persons, and all our participants to Organic Semiconductor Innovations, a faculty development initiative. I'd like to invite Professor S. Nagarajan, Head, Department of Chemistry, School of Basic and Applied Sciences and Dean Academics, CUTN, Thiruvurur, to welcome the gathering.
Good evening to all. So at the outset, I'm very happy to invite you all to this first session of the faculty development program. So this theme, the organic semiconductor, was conceived because our department, we are working on design and synthesis of organic electronic materials. So that prompted us to apply for this FDP, the AICTE, and it has been shortlisted. So, and we have received about 145 applications. People have received. That's the positivity of this program. And as far as the Central University of Tamil Nadu is concerned, we have it is placed close to Tanjavur. It is about 60 kilometers from Tanjavur, and we have a very beautiful green campus of 517 acres land. The Central University of Tamil Nadu, though it is about 10 years old, we are offering 64 different programs under 28 departments. So that is the about our department. The Department of Chemistry is the one among the 28 department. We are offering integrated masters and PG diploma, PG program, PG diploma as well as the PhD programs. So today for this FDP, we have a with the Department of Chemistry for all the activities and being with us. Welcome you, sir. And whenever we talk about organic electronics or organic electronic materials in India, the first name, if you search, it will come immediately, Professor Satish Patil. So he's such a kind of a person from the, actually, I think SAR is the seedling for many of us, because we used to follow his work. SAR is working on diversified areas, and we also try to mimic or try to see that kind of work, and we are also
ఇంకేంటుండ్రు కదా సార్ ఇంకేంటుండ్రు కదా సార్ ఆపోజిట్ కదా సార్ అవును సింగర్ ఏంటి కదా
I think Professor Nagarajan, I think his connection is he got yes, Professor Nagarajan, go ahead now. Yeah, now we can hear you. Yeah.
So organic semiconductor is an important area of So the government of India as well as the international bodies, they are pumping enormous amount of money for developing new materials, new organic materials for electronic application, because it has many advantages. So I'm very happy to invite Professor Satish Patil sir, because he will be highlighting about the importance of organic molecules in the present day electronics. So very happy to welcome you, sir. And thank you very much for accepting our invitation. And I'm very happy to welcome all the participants across the country. I welcome my colleagues. I welcome Dr. John Prakash and our research scholars. Welcome one and all. Now it's over to Anupama.
Thank you so much, sir, for explaining the importance of organic semiconductor devices to us and for welcoming the gathering. I'd like to invite Dr. John Prakash, Assistant Professor, Chemistry Department, Central University of Tamil Nadu, to tell you more about the ATAL Academy-sponsored Organic Semiconductor Innovations FDP. Sir, please.
Yeah, thank you, Anu. Respected Registrar of the University, Professor R. Thirumurugan, sir. Our esteemed Chief Guest and eminent speaker, Professor Satish Patil, sir. Professor S. Nagarajan, Coordinator of the ATAL FDP, distinguished faculty members, and my dear participants, sir. Good evening, everyone. It is my pleasure to extend a warm welcome to all of you as we board on this exciting journey of knowledge and innovation through 6-day online FDP on organic semiconductor innovation, a faculty development initiative. This FDP is being organized by the Department of Chemistry, Central University of Tamil Nadu, under the esteemed aegis of ATAL Academy. As many of you know, the ATAL Academy, established by the All India Council of Technical Education, has been at the forefront of enhancing the professional competencies and subject expertise of faculty members across higher education institutions in India. Through a multidisciplinary approach, this initiative is committed to raising the bar for research and innovation in cutting-edge fields such as organic semiconductors. Over the next 6 days, participants will be immersed in a rich program that includes 13 expert lectures. 7 of these sessions will be delivered by distinguished academics, including 2 renowned resource persons from international institutions, complemented by 6 sessions led by accomplished industry experts. Together, these sessions aim to provide an in-depth understanding of the foundation principles, the latest advancements, and innovative applications of organic semiconductors in modern technology. We are happy to announce that this FDP has garnered participation from 145 attendees nationwide, including faculty members, research scholars, and postgraduate students. Participants span over 20 states of India with 121 faculty members in which 44 are from AICTE approved institutions, 16 research scholars, and a postgraduate student. Notably, 70% of the attendees come from engineering background, reflecting the interdisciplinary appeal of this topic. To ensure a meaningful learning experience, participants will receive an e-certificate upon successful completion of the program. This includes submitting feedback and achieving a minimum of 70% in an online MCQ-based exam, which is scheduled on 14th December 2024. I am confident that this program will serve as a dynamic platform for fruitful interactions, knowledge exchange, and professional growth. Let us work together to make this FDP a resounding success. Once again, I extend my best wishes to all the participants and express my gratitude to our distinguished speakers and organizers for this unwavering commitment to excellence. Thank you, and I wish you all a highly enriching experience. Thank you again.
Anupama,
You are in mute.
you are in mute, Anupama.
Thank you, sir. Now I'd like to invite our chief guest of the day and Registrar of Central University of Tamil Nadu, Professor R. Thirumurugan, to deliver the inaugural address. Sir, please.
Respected Professor Nagarajan, Head and Dean, Academic of Central University of Tamil Nadu, and respected Dr. Satish Patil, and also the members, that means experts from the various institutions, and my dear participants. I am very happy to be here to inaugurate the AICTE training and learning of the ATAL Academy sponsored the 6 days online faculty development program, the Organic Semiconductor Innovations, a faculty development initiative. It is organizing by one of the CUTN icon, that is the Department of Chemistry. So I know the FTP programs, so various department and various institutions applied for this FTP program. So that very tough competitions, so that our CUT received for only the chemistry department, Professor Nagarajan and Dr. And also the Dr. Vittal Babu applied for the programs. And also happy to note that so that the Organic Innovation FDP funded by the AICTE in New Delhi. So I am always feel very proud and happy to whenever I attend any program organizing with the Department of Chemistry. So that is the chemistry department, one among the best and potential department of Central University. So I hope you all are our CUTN website says that each faculty members having for the well reputed and well expert from this various field of the chemistry departments. So I come to today FTP programs. So that is the morning I met Professor Nagarajan. He said that it's the overwhelming response from the various participants. So that means the 138 participants from the 20 states. And also the resource person from the 2 international and 6 from the industries and 6 from the premier institutions. So all are aware of this government of India now promoting for the semiconductor. So like the Semicon India achieved the unprecedented result. So that means that even for this mass gathering, like for the 250 plus exhibitings, and also for attracting the 10,944 visitors from the 42 countries. So our Honorable Prime Minister Sri Narendra Modi ji preside over the functions, inaugurated ceremony of the Semicon India. So based on these programs, so all are the well-versed and also well exposed through this event. And also for the semiconductor chips, or the heartbeat of the digital age. So, and also for this, the program like the FDP is the very important one things. So normally you know all very well about the semiconductors. The semiconductor is the wearable for the technology and also play a crucial role in the managing the connectivity and enabling the transmission of the gathered data and the paired devices such as smartphones or computers and also for the so on. So that means very particularly for this, there is the automated delivery robots and semiconductor chips and handle data from the GPS and obstacle detection sensor, allowing the robots and navigate the routes and deliver the package efficiently, not only in the chemistry and across the field of the various, as well as the biological and physical and chemical, like that. And also for these programs is the promoting the indigenous intellectual property rights and the generation and encourage and enable the incentive transfer of the technologies. And also I hope the program is for the enabling collaborations and partnership programs with the national and international agencies, industries, and institute for catalyzing the collaborative research. That means the academia, industries, and also for the commercialization as well as in the skill development program. I hope this FDP will be fulfill your expectations. So from the expert from the various reputed institutions, so across the country as well as the abroad also. So I wish you all the participants to inculcate the more knowledge from this FDP. I wish you good luck all the participants. And also I am very happy to this. Congrats to the chemistry department as well as the Professor Nagarajan and his team members. And also I thank the organizer for providing the opportunity to inaugurate this the very valuable and wonderful FDP program. Thank you so much. Thank you.
Anupama, you on mute again. Unmute, please.
Thank you, sir, for your kind and inspiring words. As we come to an end of the inaugural session, our first plenary lecture will be delivered by Dr. Satish A. Patil, Professor and Chair at IISc Bangalore. Before moving on to the session, I'd like to introduce our resource person, Dr. Satish A. Patil, to you. Sir completed his PhD in Germany and has been working as a professor in IISc Bangalore from 2011. He has also worked as doctoral fellow in the University of Wuppertal, Germany, and as a postdoctoral fellow in University of California, Los Angeles. He has been a recipient of several awards and honors such as Swarna Jayanti Fellow, Young Affiliate of the World Academy of Sciences, INSA Young Scientist Award, and many others. Sir, we welcome you to the FDP program, and I hope everybody is able to learn a lot from you today.
Thank you very much. Let me share my screen. Yeah, first. Just a minute. Yeah, let me know, Anupama, when you are seeing the screen.
Yes, sir.
Yes, sir, we are able to see the screen.
Yeah, okay. All right.
Yes, it is working, sir.
Yeah, so we'll go. Is okay, unable to go to. Okay, let me have to share one more time my complete, perhaps hide. Yeah, it's because just a minute. Give me a second. Okay. Entire screen. And let me know as soon as I go to a full presentation here, okay? Are you seeing full presentation now?
Yes, sir, we are able to see
Okay.
the full presentation.
Oops. Okay, all right. Let me just take laser pointer. Okay, so let me first, I hope I'm audible now. Yeah, so let me first begin with thanking Dr. Nagarajan and, of course, Central University of Tamil Nadu for giving me this opportunity. I do consider this is a great honor, and I will be happy to teach you because what Dr. Nagarajan had requested me to teach very basics. So this is a faculty initiative program. What I will try to do is I will not show much of the work we are doing it. It is little bit at advanced level, but I will try to give you very, very basics in fundamentals and emerging applications of organic semiconductor, why this field is very, very important, what are the current applications people have already demonstrated by using organic semiconductor, and what are you going to really see in future emerging applications. So this is the main sort of a motivation of my talk, and next 90 or whatever 60 minutes I will try to go through step by step how this field has emerged. So you see that first, like, let's look at how materials have shaped a human civilization and how organic semiconductors has played a very, very important role of shaping electronic devices, what we see, what are we using today. So this is what the picture, what I'm showing is world's first computer. You see, this is a gigantic, equipment. You need several processors to operate the world's first computer, and you need a massive space to accommodate this computer. You see, this is the European lady who is standing more than 6 feet. So you need a large number of processors to process a very small, tiny amount of data. So the capacity of this computer was very, very, not very slow, and this computer could not really work, with very high speed. But however, look at what happened in today's computer. Today's computers are very tiny bit of a device. They are flexible. In some cases, they are indeed flexible, and they store a gigantic amount of data. So there is indeed a major transition happens in the computer because of the range of devices or miniaturization of this device. A massive, such a gigantic device has been converted into such a small, tiny device. Now we can carry these computers in our bag, and you can connect to the rest of the world and process a large amount of data. So the question is, what leads to this transition? So why this world's first computer become such a tiny device. And what I will emphasize here more is the role of organic semiconductor. How organic semiconductor have played an important critical role of converting such a massive computer into a small, tiny computer. So this example, I will emphasize more what is inside and how we can really think about role of an organic semiconductor. Similarly with the cell phone. This is again a world's first cell phone. This is, Dr. Cooper in Motorola was also delighted to speak to his colleague to the next room. You see that this cell phone, a weight of this cell phone is 3 kilograms. It's a massive, gigantic device. And, he could not really connect to a long distance. But however, talking with colleagues in the next room itself was a big deal. But now you see what happened to the cell phone. There is again a major transitions in a cell phone. Now today's cell phones weighs in a gram, and they are very fast, devices. These cell phones also can now serve, as good as computers. They process a large number of data, and now we can exchange information across the globe. And this has made a major dramatic change the way we are perceiving the knowledge as of today. Because as of today, a person in a very interior India can do a coursework which is running in MIT, Harvard, or Cambridge, in any top institutions. So this cell phone has helped to distribute the knowledge across the globe in a different part of the world. And this indeed is going to play a very important role for the growth of Indian economy in coming futures for next 20 years. You can imagine a large number of kids having a similar information, for to learn new things, advanced things, and they are going to compete best in the world by using this one. So indeed, this kind of a transition in the internet, in a computer devices, is going to impact massively a growth of Indian economy across the. Of course, it's not only India, but it is going to help a lot of people who are. There's no sort of a disparity in wealth distribution. Now people are going to compete across the globe by using. This is something which is in the context of economy. But the question is this faculty development program is mainly focused on organic semiconductor. Now maybe you may be wondering how organic semiconductor played in this role. What is the exact role of organic semiconductor? Let me walk you through what is inside these devices now and how organic semiconductor played a role. Let's look at role of semiconducting materials and how, because initially there was a lot of research has done, people have done for on a conventional semiconductor like a silicon. But in a recent time, people are increasingly using organic semiconductor because some of these screens, you see the display screens, are integrated with organic light emitting diodes, and there are other transistors are made with, of course, still with the conventional semiconductor. Let's open the cell phone now and see what is inside the cell phone. All of us are carrying cell phone, but what is inside the content? Why these cell phones are such a powerful machines altogether? Let's open the cell phone and try to understand. Let's look at display. The displays are amazing today. Actually, you can see with any viewing angle, the cell phone display is really as good as for example, a display you see in a monitor in other devices. But however, this has not really taken a birth overnight. There are people who have worked for a prolonged period of a research and development in this area. For example, developing blue light emitting diodes was a big challenge. Blue light emitting diodes required a wide band gap semiconductor, the semiconductor which has a band gap of more than 3 electron volt, and those are extremely challenging to achieve a semiconducting material which is stable, give a very high efficiency in a blue part of the wavelength. So developing blue light LEDs was a challenge for a very long time, and there are until now 3 Nobel Prize awardees have been awarded in physics for developing blue LEDs based on gallium nitride. So similarly, radios, communications. So here also, I'm not an expert in communication, but however, communications has become very smooth, and there is no noise. Voices have been very clear. Even you are talking about a WhatsApp on a friend in America or any part of the world, you see the radio communication has improved a lot, and that also has led to 2 Nobel Prizes in physics in 1909, and then 3 Nobel Prizes awardees in physics for developing transistors as well as integrated circuit, which I will talk a little bit about the transistors, how first transistors was invented, and what are the main characteristic of those transistors. Similarly, with the GPS, again, you see that as of today, we do not, the Google map or any map is so convenient for all of us. We can reach to any part of the world without asking anyone. In the past, when we were traveling, or if you go to the location we are not very well familiar, we have to keep talking with local people and asking how to reach to the particular location. But however, Google Map has now, the navigation has become so easy where you can reach to any part of the world by just following the Google Map. And there was a Nobel Prize in Physics in 1921 for improving the accuracy using relativity theories. There's a lot of mathematics has been done how we use relativity theories to to improve the accuracy for a location. Cameras, as I talked about it, you see there are beautiful cameras. Many of our kids actually today are using these cameras. There are also Nobel Prize for Physics in 2009 for CCD light sensors. And batteries. What kind of batteries we use in cell phone? Today you use lithium batteries, but you see these devices are, some of the devices you don't have to charge very frequently. In the past, we have to charge these devices very frequently, but now the battery lifetime has prolonged by introduction of a very compact battery for small devices. And those in 2019, Nobel Prize was given for invention of lithium batteries, because lithium electrodes were invented and they have been developed from last 50 years, and now they converted into a powerful battery. So this is what some sort of a research has gone in to convert a previous device, what I talked about it, convert this device to this device. So one has to be very careful about implementing new technology. It requires a lot of patience and time and a lot of R&D efforts. So that's a summary of these slides, and then how organic semiconductor play out. Let's look at the transistors. I don't know, many of you must, I don't know how many of you know Bell Labs. Bell Labs, there are many inventions happen in the Bell Labs. Bell Labs produces large number of Nobel Prize winners, and it's a laboratory where it really promotes the interdisciplinary research. People coming from a different background, they do work in Bell Labs. So this was the first transistor. Transistors were developed by Bardeen and Shockley and Breitheim in 1947. You see the transistors that totally changed the world, but the transistors, when they invented first time, you can see the kind of semiconductor use. This was again a very big transistors, and kind of transistors we are using in cell phone today. There are millions of transistors we integrate today on a cell phone, and those transistors you can't even see with eyes, because we integrate so small tiny transistors. And now with the invention of organic semiconductor, you anticipate you can print these transistors on a large scales on integrated circuits, and that boosts the efficiency. Transistors plays a very important role of increasing speed and efficiency of your devices. So, but this is the way the discovery led to what we see today, because now we use a very different class of semiconductor. And then in future, when people start using organic semiconductor, these transistors are going to be flexible, and they can be printed on like the way we print our research paper on a printer. So we develop organic semiconductor ink, and you can print millions of transistors that will further enhance the efficiency of your cell phone or your laptop or whatever the optoelectronic devices you are using it. So in future, the invention, the transistor basic physics of transistors remains same. Okay, so this credit goes to these three guys, where they thought about this device and they invented these transistors, and these transistors lead to the change in the world. So molecular semiconductor optoelectronics, what are you going to see in future? I think some of you must have seen this picture. You see this organic light emitting diodes have been now used in television. This is a LG which recently introduced this television. You see in the past, you never see such a beautiful display of covering the entire screen. You can see from any angle. You don't have to sit right in front of a television. That's the biggest advantage of organic light emitting diodes. Viewing angle can be from anywhere. You perceive the similar quality of the image by using OLEDs. I will talk about a little bit more fundamentals of OLED in my subsequent slides, but now this is a successful story for organic semiconductor, where people are now using organic semiconductor in a commercial devices. So similarly, in monitors, people are currently using it. Samsung has introduced this foldable cell phone. We can fold cell phones by using, again, most of the component in these devices, especially the display part, is organic semiconductor. People are currently using building integrated photovoltaics. You can use a semiconductor ink, polymer ink, and integrate with your building material. This is a billion-dollar market, building integrated photovoltaics, where we have you can use it, organic semiconductor, as an ink. This will give a good aesthetics to your building, but however, it will also start harvesting the light. So these are building integrated photovoltaics. This is a building which is currently demonstrated in Germany. But again, this will eventually sort of penetrate the market, and then eventually people will have in future homes. You see that people will be integrating organic semiconductors, photovoltaic devices in a building, and they can use it for this purpose. So, as I promised, organic light emitting diodes is going to be as a $100 billion industry. This was an old data, Miss McKinsey analysis, which is more like trustworthy analysis. But in future, if you go, and this market is going to go bigger and bigger. It contains a multiple layers. It has a cathode and anode, and then hole injection layer as well as electron injection layer. But the emissive layer is here based on molecular semiconductor. So I will discuss this part a little bit more in detail in basics, how these devices works. But this is a multi-layer sandwich structures where we have anode and cathode, and you have electron transporting layer, hole transporting layer, as well as emissive layer. So that this device is not that straightforward to make this device, but these devices has been now integrated in a commercial device. Means these devices achieved a necessary sort of figure of merit. For example, these devices now show very high efficiency, very bright colors, as well as stability. So these are three important parameters to integrate before you integrate in a commercial product like this. So the research in organic LEDs began somewhere in around the 1960s. But however, it took really long time to integrate in the devices, and today some of these devices have been integrated with in a small devices. But in future, eventually, how these LEDs are going to be used for lighting applications. So that's a bigger challenge. Still, that has not been yet addressed. But how are we really going to use OLEDs for lighting applications? So let's look at again more display. This will motivate essentially for you how organic semiconductor research is very, very important. Already it is very, very important in commercial devices, but it's going to again open up a lot more applications and diversity in terms of applications. So this is a electronic display. You see what happened to the television. Some of you must have, I don't know whether, at least when I was a small child, we used to, see this cathode ray tube based television. These are gigantic television, very heavy. It requires lot of power. They used to consume lot of power, and display was very, very dim and fuzzy, very poor display. When you see a television in front of a TV, you have to go very, very close to see the actual, to make a sense of an image. But however, then later, people have introduced liquid crystal display, plasmas, and today we see a beautiful display like, for example, organic light emitting diodes. These televisions they consume less power, they give a beautiful display, and these eventually, these displays can be also foldable. So they are, sort of improved but suppose if you're watching a cricket match or any sports on this kind of a television, you see the clarity now. The clarity of images has improved dramatically. In the past, we used to see CRT, and now this has a less material, very, flexible, lightweight devices. Now we are using inside the house. But then organic semiconductor plays a very important role of transition of a CRT televisions in organic light emitting diodes. So similarly with the lighting applications, as I promise you, this is going to motivate you more and more why you should sort of do a research in organic semiconductor. Suppose this is what the lighting options we have. Some of you must have used this incandescent lamp. This is a sort of a tremendous amount of energy we used to waste. In an incandescent lamp, you had a tungsten, some sort of a fiber here, and you heat that by applying the voltage. And you use a bright light inside the vacuum. The bright, when you heat this tungsten, it will glow. It will glow at certain temperature, and inside the vacuum, you'll pass the light. This was, we used to waste 60% of energy in terms of heat. then these displays are very, very poor. Sometimes it is very difficult even to read by sitting inside below these lights. That has been changed, and the lifetime up was very, very poor. You see, the 40 watt will give 1000 hours. Okay, and it's because these, by you are turning on or glowing this tungsten, filament by applying the heat. Eventually, this one, when you cool it down, and or suddenly if you start heating, or there is a disruption in power supply, then you see these lamps have a very, very poor lifetime. They used to sometimes stay for 1 hour or less than 1 hour, whereas then to come over this, fluorescent lights were introduced, and this now you see that instead of 40 watt, you have 10 watt, but the lifetime has improved to 10,000 hours. They work, and the idea of a fluorescent, but these are again very toxic. It contains mercury in these lights. So these are also, people are trying to replace with this. Most of the light what we see today is based on fluorescent, but they are also not environmental friendly. But they are, in terms of energy efficiency, they are much better than incandescent lamp, but however, they are not very environmental friendly. So eventually people are now trying to do a transition to LEDs, where LEDs are, again, you use very less power, 1.5 watt, and you can run these LEDs for prolonged period of time, 50,000 hours. The mechanism in LED, the way it works itself it gives a lot of durability to these devices. Now the question is, as I mentioned, the cost of these technologies, for example, incandescent lamp will cost you around 10 rupees, but however, LEDs will cost you more than 300 rupees. The challenge for the scientists is now, how are we really going to make it cost-effective LEDs? And this is where organic semiconductor is going to play a very important role. People will use, at the moment, these LEDs are made based on a conventional semiconductor. For example, in these LEDs, we use gallium nitride. They're very sophisticated techniques. People have grown these semiconductor with very sophisticated methods. As a result, it leads to a very expensive device. But however, how are we really going to make this device is very cheap, and then as cheaper as incandescent lamp? This will allow this technology to penetrate deeper and deeper in market, and this will also address major energy problems. For lighting, you need a tremendous amount of power. You see that you are using 1.5 watt compared to 40 watt, and you are giving a very bright light, and one light will entirely cover a measure of your household. So this is the reason these LEDs are going to be, it's going to be an energy problem. How are we really going to replace this conventional semiconductor by using organic semiconductor and make a very efficient and bright LED? So that's still open questions, and that's an ongoing research. And there are many limitations with organic semiconductor, which perhaps I will talk subsequently in next few slides, why it is challenging to make organic LEDs and what are the major problems. So, but then all began again. Incandescent light was, you know already who is this person actually on seeing on the screen. But when he introduced this first time, people mocked about his efficiency. When everything begins with a very small number. So his efficiencies were as, this very, as good as a candlelight. For example, the brightness of LEDs we talk about in, lumens per watt. So it was when first time when he introduced this technology, that time its efficiency was 1 lumens per watt. So people mocked about what kind of light we are going to see, but eventually the same technology we use until now as an incandescent light. So this discovery is very, very important. But then he made a very important statement. So this is a famous statement where Thomas Edison made. He said, "I have not failed. I have just found 10,000 ways that won't work." Because the idea was, he looked at the entire periodic table and screened a large number of compositions and different elements to make this incandescent light, because he wanted to really make it very cost effective. So eventually he used carbon fiber, tungsten filament, n number of different compositions to make it as cheap as possible. And his discovery has really brightened the world. We use for more than 100 years Edison's discovery to light our household or different places. So this is the way it's a very profound statement. We have to learn from failures. But when you are doing a research, you're sort of doing trying to invent new things, then the failures is a major component in your research. So when you start any new research, you should be first prepared. How are you going to learn from a failed experiment? Failures is a major component of your research, where you learn from failures and try to come over those limitations, and then start researching a new ideas and invent a new problems. So for me, this is a very, very profound statement, and this is very important for any scientist to learn from failures and move forward, rather than consider as a setback in your academic growth. So let's look at what are the major advantage. Now, organic semiconductor, as I mentioned, if you compare with silicon, if you take silicons, you have to really convert a raw sand of a silicon into device. You have to really heat at very, very high temperature, and you have to really convert into single crystalline silicon to make a sensible device. Whereas in organic semiconductor, you can make ink out of these material, because organic molecules are soluble in a common organic solvents. You can take any common solvents, like it depends upon the solubility of a organic semiconductor. You can make ink out of it. So this is the ink of a different conjugated polymer. You can change the color. I think that's also major advantage. That's my third bullet point. You see, you can tune the physical and chemical properties of these material. So eventually you can use a printing technique, or a spin coating technique, or a spray coating technique, or a slot die coating. There are different ways of making thin films. You can make thin films of these materials by using this organic semiconductor ink, and you can make it a very lightweight devices. For example, this is a flexible solar cells. You can make solar cells as very flexible and lightweight devices. If we compare this with the silicon is very heavy and rigid. You cannot make a silicon by using a very simple fabrication techniques, a very flexible solar cells. Whereas the advantage with molecular semiconductor is you can use this ink and coat on any surface, and you can make it a flexible solar cells. Similarly, on organic LEDs, you can coat on any surface. For example, you have a curved surface. If you are using in a application, like if you are coating something on a car, or for example, your floodlights on, we are coating on any surface, you can coat on such curved surface and use organic light emitting diode, molecular semiconductor based ink, and then you can coat on any surface, and you can make that surface very bright. So this is the major advantage. But however, everything comes with pros and cons. For example, I will explain you what are the major limitations as of today. If you're an organic chemist in the audience, actually, so you know that these are the simple materials. You see these oligoacenes, which are fused aromatic these benzene rings. You can use, these are wonderful semiconductors. You can use oligothiophene. These are all small molecules. You see rubrene, for example, you see this perilene diamine. There is C60, TTF, this tetrathiophulvalene. So this is a small molecular based organic semiconductor. There is another category which works in a polymer. So organic semiconductors are divided into two different classes. One is small molecules, which are, this is the one, a range of derivatives, you see that. And you can polymerize some of these molecules and make it a large, gigantic molecules. So polymers, and what is the major difference now? In terms of property, they differ significantly. For example, small molecules, it is difficult to cast a thin film from solution, because the viscosity of these molecules is not as high as polymers. So these materials, we have to thermally evaporate and make a semiconductor grade thin film. And however, in case of polymers, you can use these materials and dissolve in a common organic solvent, and make a very high viscous solution. And that viscous solution you can coat on any surface. So that is the major difference. You see that the difference between organics in terms of properties, you can grow a single crystals of these small molecules. So growing single crystals of polymer is also possible, but however, it is very challenging to grow single crystals of polymers because these materials have a sort of a large polydispersity index. Every repeating units are not very similar. So as a result, it is difficult to grow a single crystals of polymer. Whereas in small molecules, you can grow single crystals and then you can really get rid of some of the structural disorder. So there is a difference in terms of the transport properties. For example, the mobility of these small molecules is charge carrier mobility. As small molecules is slightly higher than polymers because polymers contains more defects compared to the small molecules. So you can always, there is a clear distinction between a small molecule and polymer. But the beauty of this one here is you can tune the property. For example, trans-polyacetylene and polyfluorine, there is a major difference in a band gap. Here we have a band gap of a less than 2 electron volt, and here the band gap is close to 3 electron volt. And in case of polythiophene, if you use heterocycles, for example, these, in heterocycles, when you use the band gap is, falls under 2 electron volt. So you can tune the property as an organic chemist. You can tune the physical properties as I mentioned in the previous slide. Tunable physical and chemical properties. That is very hard to do in case of a silicon. You can dope it, you can change the band gap a little bit, but you cannot tune the property like this. So this someone is unmuted. Can you mute, please? Yeah.
Mr. Rajkumar, please mute.
Can you mute him?
Mr. Rajkumar, please mute. Rajkumar? Rajkumar? Mr. Rajkumar?
Is muted now?
Yes, sir. Yes, sir.
Okay, fine. All right. So going forward, you see that basically, eventually, you can now distinguish these two classes of semiconductors, small molecules and polymers. But then now let's try to understand the basics of these things, how the bands are formed, why the electrical, optical properties are very different compared to a conventional semiconductor. Conventional semiconductor, if you take a silicon, it's a three-dimensional semiconductor, and you see that they form a very well-defined bands, okay, by the conduction band and valence band. And this is the distribution of the bands in case of a conventional semiconductor. Whereas in organic material, if you learn a molecular orbital theory, you have discrete energy levels. You do not have this well-defined band. So that's a major difference which is between the conventional semiconductor and a organic semiconductor. In organic semiconductor, you have discrete energy levels, whereas in a conventional semiconductor, you have very well-defined bands. That changes the property. Eventually, this band structure, electronic structures of an organic semiconductor, the physics, which is, well-defined physics, people have documented in textbooks. You have to be very careful when you are borrowing all the physics and applying the similar theories for organic semiconductor. In case of organic semiconductor, you have discrete energy levels, you have disorders. The disorders can kick in from from a different pathways. Just give me a second. I have a low battery. I will connect my battery. Now, Dr. Nagaraj, give me a second.
Please, sir.
My sincere apologies. I'm just connecting the battery. All right. Okay. So this is the major difference. You see that between a conventional semiconductor and a molecular semiconductor. So now let's try to understand. So this is very basics. So how we can really learn actually what happens to the electrical properties and optical properties, because the band structure is very, very different compared to this one. And there are other problems in a molecular semiconductor. So this is the repeating unit of a polymer. You see that you have intra-chain coupling in these polymer as well as interchain coupling. Interchain coupling is essentially based on the interchain interaction between the polymer chain is very purely van der Waals interaction. So these are very weak interactions. Whereas in case of a three-dimensional semiconductor, you have a covalent bond between these chains. So here you have intra-chain coupling and interchain coupling, and these interchain couplings are very weak. So essentially, when the charge carriers move towards by this backbone of a alternating double bond and single bond by this pi electron cloud, where you see that the charges will hop across the chain. So the transport mechanism in these kind of a material is by hopping, not from a band-like transport. So then in conventional semiconductor, you have very less disorder, whereas in this case, we have a disorder kicked in by various means. For example, there is a structural disorder, there is a disorder due to chain conformation of the polymer, there is a disorder due to the weak coupling between this inter and intra-chain weak coupling. So there are numerous parameters which controls the transport properties of these polymers, and as a result, it's very difficult to attain the high mobility, high charge carrier mobility. As a result, when you make any device based on organic semiconductor, the efficiency of the device is poor as compared to a conventional semiconductor, because your charge carrier mobility is inherently lower compared to the conventional semiconductor due to these defects in a structure. So let's try to again a little bit understand more how these bands are formed. You see that, as I mentioned, you see from ethylene to polyacetylene. If you go, this is the way the hybridization takes place in organic semiconductor. You see this, you have a pi bond. These are this PZ orbital, they overlap. Then you have alternate single bond, double bond. You have a sigma bond and pi bond. A sigma bond, pi bond. In this, due to this, you have a pi bond cloud because of this PZ bond overlap, and you get a sort of a transport through these kind of a chain via these alternate single bond and double bond. When you bring such a large number of a alternate single bond together, you form some sort of a kind of a band, but these bandwidths are very, very minimal. There are no bandwidths in principle, and you form a HOMO and LUMO. Eventually, the bands open and you form some sort of a semiconductor in this material. When you dope it, you can increase the conductivity and you can use in any kind of devices. So this is very basics, how the bands are forms and what is the transport mechanism in these materials. You see that already I have shown a different example here. There is something called density of state. If you are not a physicist, you have to just go back and see what is the density of states means. The density of states in these materials is a Gaussian distribution. You see, this is the small molecules and this is a polymer. You see, this is a precursor of a PPV. In the past, PPV people will make this polyparaphenylene vinylene material via precursor route, because your polymer has to be soluble to convert into PPV. Eventually, people started introducing these alkyl chains, and these alkyl chains are a insulating chains. They do not participate in transport mechanism. But however, they increase the solubility. For example, if you compare the polythiophene and compare to P3H-T, this is also polythiophene, but however, at third position, these are the lone pair of a sulfur. You introduce such a alkyl change to increase the solubility of these material. And as a result, you can, build a molecular weight with very high number average molecular weight and with very tight polydispersity by playing with a solubility. Whereas in this kind of a polythiophene, you don't get a very high molecular weight because the polymer precipitate out before it start and you stop growing actually further. So you don't really build without solubility of a polymer in a common organic solvent. You don't really build a very high molecular weight material. So that limits the property of a polythiophene. Similarly with pentacene. Pentacene is very unstable material. And you introduce this TIPS group here. This becomes a TIPS pentacene. In small molecules, you increase the solubility. And then you can really make a devices out of it from a solution. So, but it has its own sort of a downside of introducing this alkyl chain. As I mentioned, these alkyl chains, they do not participate in transport mechanisms. So that's the reason one has to be very careful about length of these alkyl chains. So these alkyl chains should not be very, very long. Then they introduce the defects in structures if they're very, very long, because the interspacing between the polymer chain becomes larger and larger. Then for the charges to hop from one chain to the other chain, you need a large number of activity, increase in activation energy, and then you have sometimes the charges get very localized, and then you have defects in structures, because you see that these are each blue line here. What I've shown is the charges are hopping from one place to the other place. So you required very high activation energy from the charges if we have a very long alkyl chain. So one has to be very careful the position of these alkyl chains. For example, in case of polythiophene, very cleverly it was introduced at the third position so that they don't inhibit the charge transport, but however they increase the solubility. So organic chemistry plays a very important role here. So here, it is not very sort of easy to identify the positions where to introduce alkyl chains and how they participate. So rational design of these polymers is very, very important to control the charge transport and increase the solubility. So there is always a trade-off. You can't really make it very high molecular weight polymer and you make it very highly soluble polymer. If the charge carrier transport properties of this polymer is very, very poor due to defects, then that polymer is not going to be good polymer for making devices. So one has to really optimize very carefully to increase the solubility as well as without optimizing the charge carrier transport properties of these semiconductors. And that's a big, big challenge in the field where always people have to really carefully design. Otherwise, you have to keep doing trial and error basis. You make polymer, you measure properties, but then it is very difficult to sort of rationally conclude what limits the mobility in for these polymers. So one has to be very careful about selecting the position to introduce the alkyl chain and the length of these alkyl chains. So this is one of the major problem in the field at the moment, where optimization of synthesis is very painful, and you have to keep on doing it to identify the best material. So but however, there are advantages. As I mentioned, there are many, many advantages in these things. But first of all, you can tailor the optoelectronic properties. When I say tailoring optoelectronic properties means you can tune the homo-LUMO gap of these materials. You can coat on a very large areas. Low temperature means low temperature means you can do everything. The processing can be done at room temperature. Whereas when you see similarly, when you make a device by using a silicon kind of a semiconductor, you have to process everything at very high temperature, above 1000 degree. You can process from solutions. These materials are soluble. As I mentioned, you see that you can introduce such alkyl chain. You can dissolve these materials in any organic solvent, and then you can process from solution. You can do roll-to-roll manufacturing because you can use printing methods. For example, you can use slot die coating. You can use various other printing methods, because this is essentially ink of a semiconductor. And then you can do roll-to-roll manufacturing on a large scale, so that becomes very cost-effective. Lightweight, because as I mentioned, I will take one example of organic photovoltaics, because these materials have a very high extinction coefficient. So they absorb a lot of light, and you can make 100 nanometer thin film and we can make a wonderful device. Whereas in case of silicon, which is not a very good light harvesting material, you have to make it a very thick cells to harvest more and more light. Whereas in this case, you can use a very thin layer of a coating of a die on any surface, and you can use a thickness of in the range of 100 to 150 nanometer to make a very high efficiency device. So overall, the weight of the device is very light compared to the conventional semiconductor. And then you can also make it very transparent devices. I think that's what it's going, organic semiconductors are going to play a very important role, where we can make it very, very transparent devices by using very, very thin layers of organic semiconductor, and we can make it transparent, solar cells. So, but there are disadvantages. Where are the main challenges, and what are the research gaps now? One of the major problems with these materials is low ambient stability. As you see that these materials are based on carbon and hydrogen and heterocycles. So you can easily, if you're exposed to the light for a prolonged period of time, these materials can undergo side reactions. For example, you have a lone pair of a sulfur. It can really get oxidized if you have a very harsh conditions. So the stability of these materials is very, very poor. These materials are prone to a different kind of a side reactions. For example, they can easily undergo redox reactions. And one of the major problems, I will explain a little bit more. This is a more involved concept. The second bullet point, what I'm talking here, these are strongly bound excitons. These are Frenkel-like excitons. This is the name of the scientist who, sort of first time explained what is this bound pair of excitons. So these are electron hole bound pair. Perhaps I have subsequent my slides. I will clearly explain what is excitons means and why they are tightly bound. The diffusion length, when you say excitons, it's a neutral particle. The diffusion lengths are very, very short, 5 to 20 nanometer. That limits the thickness of the solar cells. You cannot make it very thick solar cells by using this material. Charge carrier mobilities of these materials is very, very low. For example, if you see that crystalline silicon has more than 1,000 centimeters square per volt second mobility, whereas a polymer, this is one of the best polymers, perhaps is coated because it's way less than even 0.1 centimeter square per volt second. So due to disorder, which I little bit talked about in my previous slides, where the polymer has a large number of disorder, these materials are, that's the reason the mobilities of these materials is very, very low. They are also difficult to obtain very low band gap material. Silicon band gap is 1.1 eV. When you shrink the band gap of a polymer, you make it these energy levels HOMO and LOMO smaller and smaller, and you make materials polymer semiconductor less than 1 electron volt. These materials will undergo some side reactions. For example, it is very easy to oxidize a low band gap polymer because you are changing ionization potential and electron affinity of these materials. And yet, these materials, when you make very small band gap, then it will undergo a side reaction. So it's difficult to obtain low band gap materials. Majority of the organic semiconductor people use as of today, they have band gap are in a slightly higher than 1 electron volt. That it's very hard, difficult to make a organic semiconductor which is stable at ambient conditions, and the band gap is less than 1 electron volt. It's a bit challenging to make it because of these many side reactions. As an organic chemist, if you're an audience, you understand that if you make ionization potential and electron affinity small and small with respect to vacuum, you have a lot of side reactions, and that's it becomes very, very difficult to make it. Unlike for example, inorganic semiconductor, silicon has a low band gap, 1.1 eV, but it is a very stable semiconductor. So let's take one example. Actually, I will give you one example of one device, then I try to understand. Let's try to make a solar cells. Okay, when you make a solar cells by using organic semiconductor, there are various steps. So this slide talks about how do you make solar cells by using organic semiconductor. What I have shown here, if I see my laser pointer here, you see this is a spectral irradiance and wavelength. What you get from a one sun means the sunlight is a distribution of a wavelength. You get light in a different parts of the spectrum. You get a less light, which is a UV part of the spectrum, approximately less than 2%, because these are high energy photons. You do not want to have a large portion of this light hit to the planet, because this can really penetrate your skin and it can cause a skin burn. So this is a very high energy photon, and we see that you see very often there is an argument of a ozone depletion. Ozone depletion, can really penetrate UV light towards planet, but when they pass in environment, this UV light has been absorbed majority by ozone. So you don't get a large number of photons in this range. Even this range of the photons are they also damage these organic semiconductor, because the energy of these photons is very high. They can cleave the bond between carbon and hydrogen, or carbon and nitrogen, carbon sulfur. So these are not really a useful light in terms of when you are making a photovoltaic device. So you do not want a material to absorb in this part of the wavelength, and you do not want this to be with very high intensity. So majority of the light you see, as I mentioned, this is the solar emission spectrum, what we are seeing here actually. You see the light also majority of the light comes in the visible part of the spectrum, where we have 400 to 700 nanometer. This is a 47% of major component of your visible part of the spectrum. You see a 47% light here. And you also see a light which is coming from 700 to 1100 nanometer. This is a IR part of the light, which we call it a near IR. And you see a major component of the light. Now, when you make a device, what I have shown here is a sandwich structure between the two electrodes. You have a colorful organic semiconductor. It is always difficult to make, have a photoactive layer covers a spectrum from 1100 to 400 nanometer. It's difficult because maximum, as I mentioned, first of all, in organic semiconductor, it is very difficult to make a low band gap semiconductor because they are not very stable. So typically you make an organic semiconductor, slightly higher band gap than one EV. They typically absorb invisible part of the spectrum. Now there is already a huge loss mechanisms to begin and to make a cell. So that's the reason it is very difficult again to make a very high efficiency cells actually in organic semiconductor. So this is more like a light management. That's the reason the first step of converting a solar light into electricity is absorption of a solar light. We have to be very careful about designing the organic semiconductor which harvests the light in this part of the spectrum. You to maximize the absorption without damaging the semiconductor. So that's very challenging. So I will show you some ideas how people make it actually, or how we are making it in IISc, how we design semiconductor to harvest the maximum light and minimize the stability. So absorption of solar light is a very key step, and then you creation of a free charge carriers. So this is like a little bit more physics. When you shine the light, you generate a hole in electron. You excite the electron in the excited state, and here is your hole. But in organic semiconductor, due to very low dielectric constant, these hole and electrons are bound pair. So you cannot screen out something called Coulombic potential between the hole and electron. So this is electrostatic attraction between hole and electron. You excite the electron in the excited state by shining a light, but however, there is a very strong, force which pulls back this electron, and they are always some sort of you generate a neutral particle. And this is the neutral particle we call excitons now. Because it is in excited state, but it is not a free hole in a electron. That's what I have shown here. If you look at here, this is exciton is a neutral particle. By shining a light, you create hole and electron. But to make a photovoltaic device, you have to separate them now. You have to collect them eventually in outer circuit to generate the electricity. And this is most difficult, challenging pathway for in an organic semiconductor, where you cannot dissociate very easily because these are bound pairs. And then that's where I think we call them as a Frenkel exciton, because Frenkel is the scientist who sort of explained this physical phenomenon of excitons. So that's the reason it is called as a Frankel exciton. But these are bound pairs. So remember that. When I go to the next slide, what is the exciton is an excited state, but however, you don't really create a free hole in electron. These are bound pairs. As I mentioned in the previous, again, few slides, this transport of charge carriers to the contact is very, very challenging because these are a very low mobility semiconductor. So eventually the efficiency is very low compared to the conventional semiconductor because the mobilities are very, very low. Before you collect efficiently to the electrode, they recombine. So the recombination rate is very, very high in organic semiconductor. As a result, there is a major loss mechanism. And then you extract the charge carriers to the electrode, and that's eventually you convert into the electricity. So these are key steps from a converting solar light to electricity. The key steps are absorption of solar light by using organic semiconductor. Creation of a free charge carriers is very, very challenging. We will see how people have done it so far. And then transport of a carrier. So these are main key steps of converting a light into electricity. And it is very challenging to do using organic semiconductor. So that's the reason today, as of today, people make efficiency of more than 20% by using organic solar cells or organic materials. But however, it took really long time to understand the mechanistic pathways and come over the limitations and eventually convert into high efficiency solar cells. So a little bit more on excitons actually. So this is very basic fundamentals of organics, organic semiconductor when you should know. This is a Mott veneer exciton. You see that this is a conventional three-dimensional organic inorganic semiconductor where you have hole and electron. They are delocalized. They are not very localized on one lattice. Soon after you shine the light, here you generate a free hole and electron, and this is a binding energy of this hole and electron is 10 millielectron volt, and the room temperature energy is 27 millielectron volt. So the room temperature energy is sufficient enough to separate hole and electron. That's the reason you make a very good solar cells by using an inorganic semiconductor like silicon. However, in organic, you see now there are no bands. You have HOMO-LUMO here, S1 and S0, ground state and excited state. You see this hole and electrons are localized on some particular one-dimensional chain here. And then they recombine very fast rather than separating out. Binding energy of this one is experimentally observed binding energies in the range of 0.5 electron volt to 1 electron volt. And as I mentioned, the room temperature energy is 27 millielectron volt. So it's not possible to separate hole and electron in case of organic if you use just a single layer of a photoactive layer and make a device. They recombine, not separate it out, and you cannot make a very high efficient solar cells by using a single layer of organic semiconductor. So the radius is here around 10 angstrom, and this is actually 100 angstrom. You see that this is very, very difficult to make it, okay? And the best solar cells by using organic semiconductor. So what I will do now is I will give a little bit of a time to you guys, because otherwise I will be keep on, introducing the concept. I will open up a little bit for questions, few questions, and then again we'll move forward. Questions, please. Now you can ask questions. You raise your hand. Anyone has any difficulty to understand? You can speak. You can unmute and ask me questions. No? Dr. Nagarajan?
Yeah, it looks understandable, sir. I think it was it.
Excellent
It's okay?
presentation.
Yes,
yeah, yes, sir, yes.
Okay, fine. All right. So I'll move forward then.
Please, sir.
Yeah. Okay. All right. So I will have a few more slides to talk about it. Then I will move forward, and then again I will come back at the end of the session. Okay. Okay. So this is something which I need to go to full presentation. Okay. Now you are seeing the full screen. Yeah?
Yes, sir.
Are you seeing the full screen?
Yes.
Okay. Good. All right. So this is more like a exciton. Like as I mentioned, you cannot really Watt-Wiener excitons and Frenkel excitons. But then there are tons of opportunities. As I was asked to see where is the market for organic semiconductor. You see that organic semiconductor is as good as some of these conventional semiconductors, which is very well established. They have penetrated market, and this is the projection. Now they are going to really make it a big thing. So first, this is another, I like for sort of 5-10 minutes. I will talk about it. What is the approach people have taken to make solar cells? The first approach is called Kodak approach, where we have perylene diamide is an N-type material, okay, electron carrier, and hole carrier is this copper phthalocyanide. So in Kodak approach, they use these two separate layers, where you use a P-type semiconductor and N-type semiconductor, and they sandwich between two electrodes. And then the Kodak approach gave some efficiency. That was a 1% efficiency. And indeed, the idea is to show that organic semiconductor, they work in photovoltaic applications. So these materials are not as good as silicon, but however, conceptually, this is something called the first time Kodak used these semiconductor. Very simple. Perylene diamide, you can make in kilogram. Copper phthalocyanide is a P-type. Perylene diamide is a N-type, and you can make it a separate layer of these two, put electrodes, and it worked. But then this is a very important paper, came in 1992. It's a seminal paper in the field where people use polymer and C60. C60 is, if you are some of your organic chemists, it has a very high electron affinity. It actually take away maximum 6 electron. So the idea of here, the group up in Santa Barbara, they shine the light on a polymer like MDMO-PPV. They use this material, shine the light, they photo-excited, and they transfer the electron. Remember that I was saying that you generate exciton, and it is very hard to dissociate exciton. So this was the major, breakthrough in the field. What they observed is you can dissociate excitons and transfer the electron if you use these materials next to each other. And they found a very fast electron transfer between the conjugated polymer and fullerene. And eventually fullerene is insoluble. You can see that they introduced the alkyl chain and made PCBM. Fred Woodle in Santa Barbara synthesized PCBM, and now people are using soluble PCBM here. This is a derivative of C60. And then you see the device efficiencies improve dramatically. And this is where the current device architecture, single layer do not work by sandwiching in the electrode. Bilayer gives a slightly high efficiency, but by mixing them together, something called bulk heterojunction. Bulk heterojunction solar cells gives a very high efficiency. For example, this is a material. People mix these two semiconductors together. They use a P-type conjugated polymer and N-type layer like a PCBM, mix them together, and they get a high efficiency. So why they don't work? Single layer do not work. For example, single layer they recombine rather than separating and hold an electron. Like if you use a P3HT kind of a material, then they don't work. Bilayer, they do work because bilayer you can separate the charge carriers, but they do not give very high efficiency solar cells because of a competitive recombination pathways in bilayer solar cells. Whereas bulk heterojunction, this is the energy level diagram. You see they work very well. And today people make bulk heterojunction solar cells by using P3HT kind of a P-type polymer, or very well advanced developed polymer like a donor acceptor based PM6 polymer, with non-fullerene material, because PCBM do not participate in light harvesting mechanism. People use non-fullerene material cells, organic semiconductor, and make a highly efficient solar cells. You see the Kodak approach was 1%. Now, as of today, people are making more than 20% efficiency solar cells. This is a tremendous, transition for a solar cells based on organic. So all the difficulties, limitations which was made by Kodak first time was 1%. Then today, as of today, you see this is the animation. Now you shine the light absorption, you separate the hole in electron by using this kind of a layer and collect them. And then this is the way you dissociate excitons and generate the electrical power. And this is where I think you can make it. But however, there are other limitations in organic solar cells. For example, phase separation and stability, because these materials, they eventually phase separate. Phase separation is a big challenge in the field that really hampers the stability, the lifetime of these solar cells. These solar cells have to really, because as a function of a time, because this is a physical mixture of a donor and acceptor. You use conjugated polymer and N-type fullerene, you mix them together. But then phase separation is a major problem in this field at the moment. So people are really working out how to really freeze this phase separation and make a very efficient solar cells. So eventually going forward, there are like range of parameters what we have to work: mobility, chemical purity, regularity, and then we have to also work out the blend properties of these materials. So some of these cells, you see that like in solar cells now, people make very high efficiency solar cells by using these kind of a material. So with this, I think I will stop here. Okay. I will be very happy to discuss if you have any questions. Otherwise, I'll keep on talking and, I hope I was able to convey the idea of very basics of organic semiconductor and how to make one device at least. I talked only about organic solar cells, but each device you have to give series of lectures. So what I so far talked about it, one of the devices, very basics of this fundamental physics and synthesis of organic semiconductor. Any questions anyone has? Otherwise, I will stop here. Is that okay, John?
Just one moment, sir. Participants, if you have any queries, you can raise the hand or just put it in the chat box.
Somebody raise the hand.
Yeah.
Divagar.
Yes, sir.
Yeah,
Sir, can you hear me?
Yes, please.
Yes, sir. Can you please talk about something about doping and all, P-type and N-type? Which kind of material you will use for doping? Whether it's an inorganic or organic material only?
You can. Okay. So this is a good, interesting point, because doping I did not really talk, because doping itself is a separate lecture. Doping can be done by using both inorganic and organic. So for example, doping as of today, people are doping by using molecules only. Like for example, you can use a TCNQ kind of a dopant to do P-type doping. N-type doping is a bit challenging because the materials are not very stable. So at the moment, the physics of doping is very different as compared to the conventional semiconductor. In conventional semiconductor, you do substitution doping. For example, in silicon, you substitute with the phosphorus or boron, you can do P-type and N-type doping. Whereas in organic semiconductor, you dope by charge transfer pathways. You use the material and either you take away the electron and introduce the hole, or you donate the electron. So the doping works, by charge transfer mechanism, and you need a very large amount of a dopant. In case of inorganic material, you add a ppm level dopant and you introduce a very large carrier density. Whereas in organic, you use a very percentage, like 5 to 10 weight percent of dopant, and that gives very small, percentage of charge carrier density. So doping is not very efficient, but people are trying doping also.
Yes, sir. Thank you so much. And one more question, sir. In that bulk heterostructure, I have seen that N-type and P-types are looking like a clusters. So the band bending will be also non-uniform. So will it affect transport phenomena of excitons?
It does. But
because in conventional,
yes, you are right. You are right. See, band bending is not substantial as you see in silicon. Okay, here you have homo-lumo actually, because you see that the way the the band bending you've seen in a conventional semi, here there are no bands in principle. You have just discrete energy levels. So what defines a separation of a hole and electron is the difference between the energy gap. For example, LUMO of a p-type and LUMO of n-type. The delta E determines the electron transfer rate. Okay, so that's called charge transfer. So here, due to discrete energy levels, there will be there will be band bending is not substantial as you see in a silicon.
Thank you, sir. Thank you so much.
Actually, one question from Raghavendra. Is there any organic semiconductor based on polyester existence? Polyester.
Polyester organic semiconductor. Polyesters are in principle are insulators. For example, like polycarbonate, it is a polyester. I have not really come across anything which is based on polyester and conjugated and conducting polymer. So far, I have not really come across such example. To my knowledge, yeah.
Fine, sir. I think one question from Gopinath. Mr. Gopinath, you may ask the question.
Hello?
Gopinath, please.
Instead of fullerenes, how does it play with graphene or graphene oxide used?
Graphene and graphene oxide will phase separate because these are two-dimensional semiconductor. Those are, when you mix with polymer, the major problem is the phase separation. You don't want any phase up because you want to form a bulk heterojunction. Fullerenes form a very good bulk heterojunction. Graphene and graphene oxide, there will be polymer and graphene sheets, they will phase separate. So you don't see much of a interface between P and N type. So they do not really work very well.
Okay, thank you.
Is there any question from participants? Any more questions, sir? I think it looks no, sir. Yeah. Okay, Kishore Kumar wants to ask, sir. Kishore, you may proceed.
Kishore, go ahead. Unmute yourself and ask the question, Kishore.
Yeah.
Are you audible, sir?
Yeah, you are audible.
Yes.
So what is Kodak approachment, sir?
Kodak?
Approachment.
Kodak is a company. They just did it in first time in Kodak. Is a company.
Okay.
It's a company which makes these cameras and they.
Okay.
That's the name came from there actually. It's a scientist who was an employee of a Kodak.
Okay, sir. Thank you. The next question is, so you are explaining about fullerenes. How we are going to do organic semiconductor?
With fullerene?
Yeah.
Fullerenes are itself is an organic semiconductor. Okay, so fullerenes can have a very decent electron mobility. It is a conjugated system. Okay, so fullerene, you can dope it, you can increase the conductivity of fullerene. Fullerene itself is an organic semiconductor.
Okay, thank you, sir.
Raghavendra?
Raghavendra, you may unmute and ask the question.
Sir, good evening.
Hi, good evening.
Yeah, this is regarding the OLED material synthesis. So during the synthesis of OLED materials using organic compounds, can we make tailor-made properties during the synthesis itself? That is question number one. Yeah, that is question number one, sir. And one more doubt is, since polyester has got some conducting properties with the minor current, is it possible to synthesize polyester-based OLED materials? Is there any work that exists, sir?
See, OLED, you need to, when you are making organic light emitting diodes, the material has to be very highly fluorescent. It has to be very bright. Okay, so that's the first condition for making organic LEDs. If you are making organic LEDs, the material has to be very highly fluorescent. In addition to that, it has to have a very high charge carrier mobility. So first, if you make a bullet point one by one, what are the properties to make a good OLED? The first is the material has to have a very high quantum yield, or it's a very high fluorescent material. So esters, I don't know, the polyesters may not be having a very high quantum yield. If the material do not have very high quantum yield, then it is very difficult to make a very good LED.
Okay.
That's a major problem. But you can tailor-made property, as you ask, we can tune the properties. Yes, we can certainly tune the properties.
Okay. Okay, sir. Thank you.
Anybody else?
So one more question. Is the organic solar cells are stable at a high temperature?
They are not. They are not very high temperature is not stable, because these are all hydrocarbon, carbon, hydrogen based materials. Actually, okay. They are not very stable at very high temperature. That's what Rahul Kumar is asking, right? Yeah.
And one more
Plasma
question.
polymerization technique. Sayan Das is asking. Plasma polymerization techniques. Yes, I think we can make organic semiconductor by various techniques, because we can make it like synthesis there are many different routes. Certainly we can use it, the plasma polymerization technique. As long as you are making a conducting polymer, it's okay. As long as you have a single bond, double bond systems where you make alternate conjugated systems, it should be fine. You can make it, yes.
I hope that's the question, sir, so far. I think over to Professor Nagarajan, sir.
Yeah. So thank you so much, sir. Thank you very much for accepting our invitation without any hesitation. Just like that you have accepted. Thank you so much. And also sparing your valuable time with us.
Yes.
Thank you so much. And again, it's a beginning for this first day. You have given a very good platform. Thank you so much, sir. Thank you.
Thank you.
On behalf of all, I'll thank you. Thank you so much.
Thank you. Okay, then I will log off now. Thank you very much.
Please, sir. Thank you.
Thank you very much, sir.
Thank you.
Anu, you may.
We have come to the end of our first session. Our next session will be, let me please share my screen 1 second. Our second session is taken by Dr. Suraj Soman.
most lab, which is called the National Institute for Interdisciplinary Science and Technology. So we are based in Thirumurugan, and as the name of the lab suggests, it's an interdisciplinary lab. So we have scientists working in the area of material science, agro-processing, microbial technologies, chemical science, energy-related activities, environmental-related activities. And it's a very beautiful green campus. So if any of you are visiting to Thirumurugan, please do visit us. There are some very excellent research going on in this lab. And particularly, I need to mention that presently, like we just completed 50 years. So our Golden Jubilee celebration is on the go. So there are many activities. You can check the website. There are a lot of international conferences and a lot of Nobel laureates and those kind of people are visiting the lab. They are giving lectures and also if any of today. So as we all know, like climate change is a real threat to all of us. So that is actually the reason why, we do work on sustainability. And these are, the kind of these days, some of the searching keywords are like AI, artificial intelligence, machine learning. Along with that, one major thing is the sustainability. So wherever be the sectors that you look, you always wanted to actually have the sustainable practices. And one reason why we all look for the sustainability and this kind of thing is actually this climate change. So what I would say is that it's not climate change. It has already changed, isn't it? So we do have like around a lot of examples which is happening in and around us in the form of floods, forest fires, storms, and all these kind of events. The frequency of these events are all higher compared to what it was there before in the last decade or something like that. So one major reason is actually the increase in the Earth's surface temperature. And that has actually drastically gone from let's say close to less than 0.1 degree to all the way to 1.1 degree. And if it goes in this particular way, as per the IPCC reports, maybe in another 20 years or 30 years time, we may touch something like around 1.5 degrees Celsius. And that's actually a big problematic thing, because the moment it crosses 1.5 degree or it goes and reaches near to the 2 degrees Celsius limit, then things will become irreversible. That means if there is a rain, you will only see the rain. If there is a snowfall happening, then you can only see that. So at the end of the day, the take-home message is that life in the planet becomes almost impossible. And what contributes to it, as we all know, the greenhouse gas emissions is actually the major threat which contributes to a lot of these kind of problems. And when we look into the accountability of the greenhouse gases, almost 70 to 75% of this comes from the energy sector. That means it can be from the energy which is used for transportation, energy used by the industries, by the buildings for maybe for lighting or things like that. So, but in a general way, around 70% of the global greenhouse gas emissions are related to the energy sector. So if we want to address the climate change, we need to actually make a full stop into this greenhouse gas emission. And there, one of the first sector that we need to address is the energy sector. So conventionally, where we get the energy? We get the energy from the fossil fuels, isn't it? We dig the coal, oil, or gas, water, petroleum products, and then we just burn it out. Then we produce the energy. And at the same time, along with that, the emission is also happening. The carbon dioxide emission is also happening. So the best way to address this problem is actually moving into the renewable sector. And the best option which is available is actually the photovoltaics. Because you have, when you go to renewables, you are having many options there. One is actually the hydroelectric power. Then you are having the wind energy is there. Then photovoltaics is there. But the issue is that for hydroelectric, you need to have a rain. You need to build a dam. There are many socio-political and economic issues comes into the picture. Also, windmills, maintaining the windmills is a problem. And also, on a long run, there are other technical issues also that recently we see across, which makes it not that sustainable in a way. So considering all these aspects, photovoltaics is actually one of the best candidates to be used. And there we have the market leading technology. the silicon-based PN junction solar cell, which are good to go. Like you just buy it from any provider, you put it up, maybe 5 kilowatt or 10 kilowatt, and you generate the power, you can use it. The lifetime normally we say is around like 25 years to 30 years time, and that's fine. But at the same time, like our human nature, like as per the human nature, like we all are progressing, and we try to innovate new applications for which the need of power is ever increasing, and for that we need to actually look for new opportunities and new technologies with the photovoltaic. So there you can see that on the top you see like some of this conventional solar farms, and you need to actually find new ways like agrivoltaics, where the agricultural land can be also used for cultivation as well as producing the electricity. You can look into these kind of facades. Here on the bottom you can see that there are some colored glasses there. So these are all solar panels. So you can actually make the solar panel beautiful also. Like you can make it semi-transparent, you can make it in any colors, so that instead of the conventional window, you can actually have these kind of integrated panels, and that will add to the building integrated photovoltaics and things like that. Another major sector, upcoming sector, is space photovoltaics. Like you can actually build solar cells to be used for in the space, and in applications like drones and things like that. So now coming to the major topic of discussion for today. So I want all of you to just like look back into your home itself. Every year from each of your home, how many of these kind of batteries you are throwing out? So it can be from your remote controls. It can be from your clocks. It means if the kids are there, the kids' toys is something which consumes a lot of this kind of batteries. And in globally, out of the entire AA, AAA button cell kind of primary batteries which are not recycled, which are thrown into the Earth's crust, out of the entire thing, only 5% is being recycled. The rest of 95% goes into the Earth as landfills, and that creates a huge carbon footprint. So our area of research or our interest is to find a sustainable alternative to the primary batteries, so that at least for certain applications, we can actually replace these batteries with a alternative which is more cheap, which is more sustainable, and can be easily manufactured. So there actually I want to just mention that these days this is one terminology that you might have seen quite a lot, which is called IoT. IoT is nothing, like it's just Internet of Things. So as humans, like we do have the sense organs. We can touch, we can feel, we can smell, we can see. But when it comes to the material world, they don't have these kind of sense organs. So we put certain sensors, actuators, those kind of connectivity devices into this material world. And this comes under, the entire thing comes under this IoT, Internet of Things. So that actually finds application in consumer electronics, like smart watches, e-readers, alarms, like the Bluetooth based, like smoke alarms and smart cards, electronic price labels, n number of applications are there. So this is actually coming to the point what I have told before. The humans are advancing. Like we now live in the world with AI, ML, IoT, and all these, whatever be the new innovations, whatever we are discovering or inventing, all these need some sort of energy to be powered. And we have limited resources. In the Earth's crust, the coal reserve 60 years or 70 years. So every day we are actually inventing new things which all this energy, but the primary source of energy will only be there for another 50 years. So what you will do? So you need to actually find alternative meet the energy demand that comes on a day-to-day basis with the new developments. So there, one major area is actually, we all know that energy is everywhere, like it is around us. So how we can harness or harvest the ambient energy surrounding us. So it's actually very interesting because there are many forms of energy that we can harness, which are conventionally ruthenium-based metal complex sensitizers were used in dye-sensitized solar cells since its inception in 1991. And the semiconductor is titanium dioxide. Redox system is actually iodide triiodide system. But then, as I told you recently, with the entire development that happened with the indoor photovoltaics, with the possibility of indoor light harvesting capacity of these kind of indoor solar cells, they made a big transformation. So that has been achieved by the use of organic co-sensitized dyes. So the ruthenium-based conventional dyes were replaced by the organic dyes. The conventional iodine electrolyte were replaced by copper-based electrolytes, and introduction of some innovative new device architectures. So that has created, to the efficiencies of, let's say, the highest presently is around 15% under the one sun condition, and under the indoor light somewhere around 35% under the standard that we say, which is around 1000 lux. So here in all these cases you can see that here the researchers used organic dye. So instead of the metal complex, the ruthenium based metal complex coordination metal complex sensitizers, which are the conventional sensitizers, here you can see a donor pi acceptor or a donor acceptor pi acceptor kind of organic backbone system. So these are scalable. This actually is more easy to synthesize and also highly stable molecules. And one thing that you can observe in all these systems is that they all do have the donor unit, which is a triphenylamine. So it has certain relevance when it comes to the dye-sensitized solar cell. Triphenylamine being, kind of a starburst kind of a system, it has the capacity where, these kind of branches which are attached to the triphenylamine molecule and the orientation of the molecule prevents the spatial approach of the hole, which is present in the electrolyte, coming close to your semiconductor. Okay, so that is actually the reason why triphenylamines are used quite a lot in this kind of system. So in this regard, actually, we also are working in this area for quite a long time. And in 2017, one of the first report came for the indoor photovoltaics using dye-sensitized solar cell with an efficiency of 28.9% by the EPFL, the same group who discovered this technology or this solar cell like almost 30 years back. So they published it in Nature Photonics, and we were also closely following this area with a lot of developments in the materials, with the molecules, with the device architectures. And finally, in 2024, the beginning of this year, we came up with a very unique system, a combination of organic dyes and a dual species electrolyte, where we were able to realize the world record efficiency of 35.6. And just very recently, just last week, we actually crossed this limit and we have touched the 40%, which also got published in this Journal of Material Chemistry. I will come to that at the later point of my presentation. So it's not just the publication. Globally, there are a lot of companies who are working on in a way to translate this science to the technology. Why? Because, as I told you, the silicon-based first generation solar cells, if you want to actually put a gigawatt facility, let's say 100 gigawatt facility, you need to invest thousands and thousands of crores. It's because it's a very energy intensive process is involved. You need bigger machineries, but at the same time, these kind of solar cell, either it be polymer solar cell, either it be dye-sensitized solar cell, either it be the perovskite based solar cells, you can actually make it through simple printing process. So the use of materials are more sustainable, it's more easily available, it's cost effective, the energy which is involved in making it is also very less. So that is why now many industries are coming up and they are actually making real products for the real world. So there you can see this is one product which actually is being sold by a company called Exeger in Sweden. So we all know about the headphones, the Bluetooth headphones. So normally you need to actually charge these headphones almost every day if you are continuously using it. So they made a headphone with the solar cell which is attached to this particular neck region. So there you only need to charge it like once in a while, let's say 1 month, once in a month or things like that. Because wherever you keep the headphone, normally you don't go to this outside sunlight, isn't it? People used to go, but like it's a rare thing. Normally, like people used to sit in places where there is a shadow region is there. So some light will be available. So with that light, you can actually get the charging done there. So there is a super capacitor, there is a storage battery, there is a rest of the electronics which manages the entire power, and you can actually have a self-powered kind of a gadget. This is one example. Like that, you can have the e-readers, your mobile phones, wherever you use these kind of gadgets. Imagine that the kind of cover that you use, if that cover is made with a solar cell, which is aesthetically pleasing, it is not going to intervene with any of the aesthetics, but at the same time it is having an added functionality where it takes the light in the form of the energy which surrounds you and generates the power and support your system. So that's actually very unique, and this is the area where we are presently working on. And so now we will move into the science part. So there, as I told you, there are three major components for this kind of a solar cell. So one is actually the die, second one is the semiconductor nanoparticles, and third one is the electrolyte. So I will actually go through some of the major development that happened in these three different major components which actually come together to make this solar cell. Then, as I told you in the beginning, a transformation journey, because along with the science, this is also something, presently what the government wants, and what we all are actually targeting from the scientific communities, not just like ending up in publications or patents, but how best you can actually convert a science into a technology. So a lab to fab transition that has been achieved. Then the kind of innovative products and prototypes and the new innovations that whatever we have done. So we'll go to one by one. So first one is the sensitizing die. So what basically make a molecule a die? We can see like a lot of molecules around, isn't it? Like so what is this unique functionality that can make up a die? So there are certain criteria need to be there. So one criteria is that it should absorb the light. If it is not absorbing the light, it is not suitable for this purpose. So what do you mean by absorbing light? So that means that your particular molecule is having, it should have a band gap which is capable of matching with the kind of spectrum of light which is available. So the best one I should say is somewhere around like 1.8 to 2 electron volts. So that kind of a band gap based molecules are like the perfect ones. So conventionally, how these are being determined, so there it's not just the intuitions. So we go with the modeling initially. Then the organic chemists actually make these kind of molecules. Then we again come back and we do the fabrication of the device. So sometimes, like you make or you design molecules with certain considerations and you expect it to be like, like the world's best or things like that. But the moment you take it into a device, there are multiple interfaces. It is not just your die. You are having a semiconductor, you are having an electrolyte, and the electrolyte has additives in it. So a lot of other people are there around the die, which also influences its performance. So the final result may change. Like it may not be exactly the same like what you have modeled or like what the initial predictions has gone into. So now, like one criteria is its absorption, the light absorption. Second criteria is that it should have some binding groups. So conventional, molecules, they doesn't have any binding groups. Then it will not get. It's not possible to get attached to the semiconductor because you are having a glass. On the glass, you are having the semiconductor, and on the semiconductor, you are having the die. So you need to have certain binding groups. The conventional binding groups are carboxylic acid functionality. You can have like, pyridines, which are having the lone pair of electrons through which you can get it attached. You can use hydroxyl functionality. But out of all these various options which are available, carboxylic acid functionality proved to be one of the best in a way that the stability is there. At the same time, the electron transfer process is also much faster. So how you design a die? So initial part is like you make a conventional generic structure, which is like a donor, a pi spacer, and an acceptor. So the donor can be triphenylamines. It can be carbazole based system and things like that. And your pi spacer, normally you use thiophene based pi spacer. Then the acceptor, of course, like it's an acid functionality. So it has two roles there. One thing is to bind your molecule to the semiconductor. The second part is that your carboxylic acid, it actually deprotonates and it actually binds with the hydroxyl groups which are present actually on the semiconductor. So it's an electron withdrawing group. Okay, so there, like, you actually pull the electron from your donor to the acceptor. So that force is also required. So that has its own relevance there. Then that will be the reference type. Then you again modify the system in different ways. Like you can actually have more donors. Instead of one donor, you can actually attach two donors. So you can have maybe a triphenylamine and a carbazole together. Also, you can introduce a certain auxiliary acceptors. So benzathiazole, benzatriazole. So these kind of auxiliary acceptors, what it will do is that you can play around with your band gap. So the moment you put an auxiliary acceptor, which is an electron withdrawing group, you can reduce your band gap. So when you reduce your band gap, what will happen to your absorption? You automatically redshift your absorption. So you are actually push your absorption from the normal, let's say like from the visible region to the NIR region and things like that. Then you can do the structural engineering. So this is also a very interesting aspect where you are taking a triphenylamine. On the triphenylamine, you can actually add quite a lot of substituents. You can actually take a pi spacer, which is a normal kind of a thiophene group, and on the thiophene you can actually add certain alkyl groups and things like that. Then you can do for the co-sensitization. So this is a very new and novel approach, which has been the major game changer for the indoor photovoltaic using this kind of molecular light harvesting devices. So there, what you do is that you are having a bigger molecule and you are having a smaller molecule, and you attach these two units into the semiconductor. So you passivate your semiconductor in a way that form a very unique mono layer with this bigger molecule and smaller molecule together, and that it will act as like a kind of a wall which prevents your holes in the electrolyte coming closer to the semiconductor. So there can be a lot of dyes, like we work on triphenylamines, fused ring heterocycles like the indole, 3,2B indole, and those kind of similar systems. Carbazole, cyanine, phenothiazine, squarenes, lot of systems are there. So I will just take you to some of the examples and how that actually makes a difference. So that is where it's quite interesting to observe that when I showed you the device architecture where you have two glass electrodes, in between you have a semiconductor, a die and an electrolyte. It's a two-dimensional thing. But on a real thing, it's a three-dimensional network. And your electrolyte is closely in touch not only with the die, it is closely in touch with your semiconductor. It is closely in touch with your photoanode, which is a conductive, transparent conductive oxide coating, which is there, which is normally the FTO that we use in these devices. So, there are a lot of process like that happens inside a working device. And the moment the device see the light, you have extra electrons and holes which are formed there, and then it can move in any directions out there. And slight modifications in the molecular architecture of these light harvesters can have huge impact when it comes to the device performance. So these are a few examples where you see that on the top, these are two triphenylamine dyes, where in one of the die, you are only having one binding group, one cyanoacetic acid group, like carboxylic acid group out there. And in the other die, you are actually having two functionalities out there, like you are having two binding groups there. Okay, so in one you are having only one binding group, and in the other one you are having two binding groups. So when you attach this onto the semiconductor, you can see the way in which this is being attached. So in the one which is having only one acid group, you can see both the arms, the outside arms are actually out like like a branch, and that forms a very, very kind of strong pillar there, which prevents the holes, which are the oxidized species of the electrolyte, getting close to the semiconductor, because that is the recombination pathway. But when you go for the two attachments, there, even when you are having two carboxylic acid present there, then the binding will be very strong. Your binding of the dye onto the semiconductor is very strong there. But there you can see the issue from this pictorial representation that the way in which the molecules get arranged on the surface, your holes actually can get in between the molecules, it can get much closer to the semiconductor. So here the spatially it is away, but here it is very close. So even though your binding is better for this particular system, it is having more recombination, and finally like it creates issues. Similar way, like you can see like this TPA6 and TPA7. So you started with a simple triphenylamine and then you introduce all these changes. And here on the down you can see in a TPA6 molecule, you are having this anthracene, which is which you attach between your donor unit and your this acceptor unit. But TPA7 is a system where this anthracene unit are attached on the donor region, not on the acceptor region. And you see from the light harvesting efficiency plot here, which is the IPCA plot, that when you are having two of the anthracene unit with more better conjugation, your absorption is because you are having more transitions over there, and you are actually filling up the absorption. Because in the other one you can see there is you have an absorption around 350, then there is a dip, and then the rest is coming in. So you are having a better absorption by introducing the functionalities on a different part of the molecule. So the whole take-home message is here is that slight variations in your molecular structure can have much higher impact on the light harvesting behavior, much higher impact on the energetics, and influence the photovoltaics properties out there. So now I'll show you another example where instead of the donor, you are changing the pi spacer. So MK2 is a commercial dye. This you can actually purchase from, let's say, Sigma Aldrich or other companies. It is commercially available and is a standard molecule where you see the donor unit is a carbazole functionality. Okay, then you are having a terthiophene. There are 4 thiophenes, and in each thiophene you are having a hexyl group there, C6H13 group present there. So this is a standard system. And then your acceptor, which is a cyanoacetic acid. Okay, so from here we designed 2 molecules. We named it as YK8 and YK9. So YK8, what we did is that we keep the donor the same, acceptor the same, but the pi spacer we made it short. The purpose is we want to reduce the cost of production. So we reduced the thiophene number of thiophene groups to 3, but we changed the alkyl chain from a hexyl chain to a C8 chain. Okay. Then again we made another change into the pi spacer where we introduced a more conjugated kind of a system over there, thienothiophene kind of a system. Okay, and then we kept the same C8 alkyl chain. And what we have seen is a very interesting behavior when it comes to the photovoltaic performance. So the standard one was giving around 24%. When it comes to the YK8, it was giving 28, and the YK9 14. Then we went into, so now we get to know that, okay, there is a performance difference as a function of the molecular backbone, means mainly on the difference in the pi spacer. Then we go more deeper. So this is actually the key part. So we try to understand how the electron transfer happens at the various interfaces and probe it using various electrical and optical perturbation tools. And what we have seen is a very interesting behavior that when you change the pi spacer to YK8 and YK9, here the capacitance, this is an electrochemical impedance measurement where you actually change the frequencies and you scan over a range of potential, and you see how the electrons are being populated into your semiconductor. So that will give you your capacitance. So in both the systems, your capacitance is more or less the same. So that means your conduction band is same for YK8 and YK9. Then you measure the lifetime. So from the lifetime, you can see that the YK8 sensitizer is having a better lifetime compared to YK9. And similar is reflected in the dark current. The dark current for the YK8 is less. And the diffusion length is better for the YK8, and that improved the charge collection efficiency. So what really happened here? So YK8 dye, it is having a more lengthy alkyl chain, C8 alkyl chain. 2 of them are there. But when it comes to YK9, only 1 is there. So with these 2 alkyl chains, this YK8 was more efficient in a way to prevent the back electron transfer. That means whatever be the holes that are coming nearby, this alkyl chains used to block it in coming near to the semiconductor. And what we have also observed is that we did some very interesting photo-induced absorption measurements, PIA measurements, with and without the electrolyte system. Where we have seen it is that, like, you know, the line, the solid line represent the absorption of your oxidized species. That means you make the device without any electrolyte, you shine the light onto the device, then you probe the system, and automatically your dice will get excited, and you map the absorption of your excited species. So that is what you see here. So there you can see that there is more number of excited molecules, species which are present for the YK8 system, which is the red one, which means that the injection is more effective for the YK8 due to the energetical part. And then when you add the electrolyte into it, you know, automatically your absorption will get quenched. What happens? Because your oxidized dye is not there. Your reduced species, which is present in the electrolyte, supplies the electron, and your absorption get quenched over there. Okay, so this is the way in which we work. Like we make the molecule, we understand like what happens like when you change certain molecular functionalities, then taking it into the device, and on the device we probe the system and we take it up and understand like how the forward and backward electron transfer process and all happens. Again, like, you know, these are another series of molecules where a fused ring heterocycle is being introduced. So instead of triphenylamine, we introduce something called indole 3,2B indole. So this is also a very interesting system where you see like when you take an indole 3,2B indole, that there this particular work involves 3 different pi spaces. You take a phenyl group, a thiophene, and a furan. So, you know, with the furan, you are having a better absorption, what you see here in the blue. And with the thiophene, it is slightly less, that you see in red. And with the benzene, you can see that the absorption is not that at all great, like very slower, lower absorption there. But when it comes to the device, so when you see the absorption, what you can expect? You expect that the IID3 with the furan may have a higher photovoltaic performance. But we see the totally different situation. We see that the one with the phenyl group, even though is having a lower absorption, it is having a better lifetime and a better photovoltaic performance. So what happened there? So when you are having a furan, there, due to the lone pair of electron which is present onto the furan, the oxygen atom there, the recombination of the electrons which happens from the semiconductor is very fast. So that's why the benzene-based system is better. But at the same time, you just change the donor from a indole 3,2B indole to a benzothiono 3,2B indole. The entire thing got reversed. There, the one like previously, like where the furan is having a lower absorption, lower performance due to higher recombination. Here, the moment you change the donor, the furan actually starts performing better because there is a twist that happened in the molecule with the introduction of the furan along with. So that coupling between that donor and that particular pi spacer made some changes in that twist, the dihedral angle between the donor and the pi spacer. And that actually helped in improving the performance. Then again, like similar kind of systems, like we have also done a collaborative work with IISc, where they have come up with a triphenylimidazole based donor units. And there also we introduced this anthracene triple bond. So the entire thing is that, you know, like we can just play around with the molecule. So you should have a basic understanding about your system, like what you are going to put in your system, what is the donor, what is the pi spacer, what is the acceptor. Then the rest is actually based on the initial results and how you further modify the structure. And you need to probe very neatly in a way to understand like how the transport happens, how the capacitance varies, how the lifetime is varying in this kind of system, and accordingly you can make n number of molecules. And it's not necessary that all the time, you know, like you will get a better performance. So for example, like you can see this particular unit LGP1 and LGP3. So you are here, the donor is the same, okay, and you are having a triple bond linkage, and in one case you are having the anthracene phenyl group and a cyanoacid acid group. Okay, in the second case, the only difference is that you change the anthracene with a benzathiazole. But you see here the performance. The LG P1 is only having an efficiency of 0.13%. At the same time, the LG P3 is having an efficiency of 9%. So imagine like a slight change in the molecular backbone, how much it can actually influence the performance. So now we will move to the second category of component, which is the materials, the semiconductor material that we use. So the conventionally, titanium dioxide is used as the standard semiconductor material in all these kind of devices. So as you know, so TiO2 exists in different phase like anodized, rutile, anode. So the anodized is the most preferable phase which is used in the optoelectronic devices. So there, I'll just show you one very interesting work what we have done. So normally, the semiconductor layer, the TiO2 layer, we use nanoparticles with the particle size around 18 to 20 nanometer size. So normally when you put a 18 to 20 nanometer size particles, there are a lot of gaps or voids that will come in between the nanoparticles because those are spherical nanoparticles. So when the light is incident, what happens? It is not necessary the entire light will be absorbed by the dyes which are attached to the semiconductor. There will be some light which will go in between. So, normally what we do is that we keep a bigger nanoparticles on top of the smaller ones. So these actually will act as scattering filters. So whatever be the light which goes in between the smaller particle will get back scattered and you will get the better light harvesting properties. But the issue here is that you want to make a solar cell which is semi-transparent. You want to make a see-through solar cell which you can use for building integrated photovoltaic facade applications. So there, when you are using a larger nanoparticle, even though you are getting better scattering, that actually hinders your transparency. You are losing your transparency. Automatically your solar cell will become opaque. So there, we have done a very interesting work. One of my student, Anuja, what she did is that she made some microstructures with the zinc oxide, like star-shaped kind of microstructures. So she put those microstructures on the top of the normal semiconductor. Then what she did is that she used some acid treatment and she removed those kind of zinc oxide based microstructures. And what we were left with it is, so, like what you see here is those microstructures on top of TiO2, and once you remove it, you see these kind of patterns which comes on top of your conventional TiO2. So this actually act as scattering centers. So the advantage here is that here you are completely avoiding your scattering layer, but at the same time you are creating certain grooves and certain impressions which act as the scattering center. So thereby you can improve the performance. So the front electrode, like when you are shining the light through the front portion, through the photo anode portion, there is around 84% improvement in the performance. And from the back side, around 13% improvement. So this was actually the starting point for something very interesting that happened in our lab, where we came up with a very innovative architecture of bi-layer electrode. So one day, what happened is that this student Anuja, she forgot to remove those zinc oxide layer, and she made an electrode, a solar cell with a titanium dioxide. On top of that, there is a zinc oxide. Then interestingly, what we have seen is that there is a very huge drastic drop in performance because zinc oxide is more acidic. It creates certain issues with the dye desorption and all. But we have seen a huge improvement in the voltage. There was a huge improvement in voltage. And then we went back and then we understood that like we forget to remove the zinc oxide layer. And then we explored it in further detail. And what we have seen is that a very interesting behavior. Conventionally, the energy diagram, when you look here, this is for the normal control device where you are only having a titanium dioxide, you are having a Fermi level. The moment you put a zinc oxide on top of your titanium dioxide, there is a negative shift that is happening to the conduction band. And that is very clear from the capacitive measurement and also reflected in the voltage. You are getting a higher open circuit potential. So when you go to the control device, which is having a voltage of 1 volt, And the moment you put a bilayer like the zinc oxide, the voltage goes from 1 volt to close to around 1.13 volt, which is a huge increase. And there what we have seen is that this negative shift in the conduction band, this actually pushes the kind of trap states and the kind of surface states far away from the energetic band gap which actually comes for your electrolyte systems out there. So that actually prevents the recombination. Thereby, you are having a far better improvement in the lifetime that reflect in the performance. So this particular work was initially done with only one single molecule, which is a standard organic dye based on triphenylamine, where you are having a triphenylamine as the donor, a pi spacer, and an acid functionality. Okay, so this dye is called Y123 dye. Then what at this particular point we realized that it has a very huge impact where the bilayer electrode, there is a negative shift in conduction band that automatically increases your voltage. At the same time, there is an improvement in the lifetime. So can we try something very unique from the molecular side, which can further improve this particular aspect? So there we introduced this MS5 sensitizer. So this sensitizer is also a triphenylamine based sensitizer, but it is having dodecyl groups which is attached to the periphery, which is more effective in preventing the recombination. So by using that dodecyl group, you can see that this one is for the Y123, the star one is for the MS5. There is a couple of orders improvement in the lifetime, and that actually helped us in a way to realize a record voltage of 1.27 volt from a single junction device. So this was actually presently also the highest reported voltage from a single dye sensitized to solar cell device. And this is under the one sun condition, and under the indoor light you can see that we are able to realize voltage of around like 1 volt. So what is the importance of this voltage? And here you can see the efficiencies are not high. It is not 30% or 40%. It is only less than 10%. But that efficiency is enough in a way to power certain gadgets. I will show you here. So here, this is a temperature sensor and a clock. You can see this is a lux meter, somewhere around 1000 lux. So this is a clock and a temperature sensor you will get from Amazon, like 150, 200 rupees. So that particular gadget is being powered by a solar cell that you see here, a single solar cell with the size of, like our button in our shirts or things like that. With that size, it is able to power this kind of a gadget. Why? Because all these kind of smart gadgets all need a minimum threshold voltage of 2 to 3 volt in a way to kickstart the circuit. So here, with this new device architecture, we are able to gain more voltage. So even though the current is less, that is enough in a way to drive many of these systems. So this particular work was actually published in Journal of Material Chemistry A in 2023, and it was actually selected as one of the most popular article collection. And till this day, this is the highest voltage from a single junction dye sensitized to solar cell. So we didn't stop there. So you got the higher voltage and all, but ultimately, power matters. You need to gain more power also. So there, instead of a single dye, we introduced the co-sensitization approach. So along with MS5, we introduced XY1B, which is a larger molecule with better light harvesting properties. And then retaining the same voltage, we are able to push the efficiencies from, let's say, like less than 10% to more than 30%. And then something very interesting happened. Like, you are generating the power all the time. It's not necessary you will be using it. You need to store it. So there we came up with a new concept of photocapacitor. So where we made the solar cell and also a supercapacitor together in a one single device. So this is also a very recent development that has happened along with my colleague, Dr. Raki, where we made the light harvesting unit and also we made the storage unit together in a one single device. And presently, like, we got a efficiency of somewhere around like 14 to 15% overall power conversion efficiency with this particular system. So now we'll move to the third component. So we have seen how the variation in the dye affect the photovoltaic performance, how the variations in the semiconductor affect the photovoltaic performance, and how you can tune in. And now the third component, which is the electrolyte. So conventionally, iodide triiodide is used as the electrolyte. So this is actually one of the major area that my research group was involved in, let's say last 7-8 years time, where we introduced a new generation of copper based electrolyte. Because iodine, iodine is fine, good, easily available, but it is corrosive. And on a scale up perspective, it has a lot of limitations. So there we wanted to have an alternative. So cobalt is another component which is being used, but cobalt is a bulky molecule because it's a hexadentate system. You are having 3 polypyridyl ligands which are attached to your cobalt metal center. So it becomes more bulky. So the movement of the ions inside the electrolyte becomes a problem. So the copper-based system, so this is actually one of the seminal work which is done in this area, where one of my students, Saurav, so what he has done is that he did a very systematic investigation on iodine, copper and cobalt. And what we have find it out is that copper system is having a lower reorganizational energy. It is having faster regeneration, a better transport and higher diffusion coefficient. So here you can see the energetics. So this is a ground state excited state at the conduction band, and the conventional iodine based system is having a redox potential of somewhere around 0.4 volt with respect to the energy. And the moment you move to the cobalt based system, you are again pushing it more positive. You will have it somewhere around 0.56. And the moment you go for a copper, your redox potential is again positive. So you will get somewhere around 0.94. So now come back to the initial point, whatever I told you. What is the voltage? The voltage is the Fermi level and the redox potential. So previously you have seen that by using a bilayer device, you push the conduction band to more negative potential, you can gain more voltage. Here what is done, you changed the molecular system of the electrolyte from iodine to cobalt to copper. Thereby you can actually push the voltage. But the problem here is that the moment you reach to copper, you can see that this is actually having very close proximity with the ground state of your die. So the driving force for regeneration is very low. But even with that minimal driving force, due to certain very critical things which is there with the structural properties of this copper metal complexes, it is having very charged interfacial charge transfer thing. The thing is that, the copper, it's a tetrahedral system. Like you are having 2 polypyridyl ligands which are attached to the copper metal center. But there is a twist there between these two systems. So the dihedral angle is actually different. So due to that, the moving from copper 1 to copper 2 is much more easy. So that's why, like, even though the driving force for regeneration is very low, it is not affecting the performance. Then we went more deeper into it because our whole understanding of the system, like we want to know like what really makes copper very unique. So there what we have seen is that we kept everything the same, the semiconductor the same, the additives the same, the concentration of the electrolyte components the same. And then we took the 3 1-on-1 comparison of iodine, cobalt and copper. And what we have seen is that when you use the copper based electrolyte, there is a negative shift that happens in the conduction band. So when you are having a negatively shifted conduction band, then your driving force for recombination is automatically high. So your lifetime should be less. But what we have seen is that the copper, even though with the more driving force for recombination, maintained the lifetime similar like iodine and cobalt. So the reason is the faster kind of charge transfer kinetics that is available with the copper system, which is a molecular property, because as I told you, the dihedral angle, the twist in the system and those kind of things which are actually present with the copper, which is not there with the rest of the molecules. Then, you find out like what makes the copper unique. But at the same time, what is there still a room for improvement? What's next? Okay, so there we move more deeper and we understood, we did some trapping, detrapping measurements, and we find out that there are 2 critical issues which are still there for the copper. So one is actually the mass transport and second one is the recombination. So if you can address these 2 problems, then you can further improve the performance of these devices. So there, one of my another student, Jaydev, he came up with a very interesting study where we address one problem, which is the mass transport. So basically, what is mass transport? You are having two electrodes. In between that, you are having an electrolyte, which has an oxidized species and a reduced species. So when the whole electron transfer process happens, when you are having these bulky molecules which are present there, the movement of ions between these electrodes becomes more sluggish. So that is the issue. Then that triggers to more recombination. So there, what he has done is that he made electrodes of different thickness. And it's a very interesting study where you can see that under higher illumination intensity, that means 100 milliwatt per centimeter squared, which is the standard Bunsen condition. There, the device with a thinner electrode, which is around 4 micrometer, delivered a performance around 10%. But at the same time, when you go for lower intensity, like 1/10th of the light intensity, like 10 milliwatt per centimeter squared, there the thicker electrode performed well. Like it gives around like close to 13% efficiency. So what is the take-home message here? When you are actually going for a lower intense condition, there the kind of device architecture you need, the thickness of the TiO2 that you need is totally different from that you do for one cell, because this is a major information that actually came out with this paper, because it's a general rule of thumb that people make devices for one sun condition, and the same devices they take and they do the indoor measurement, which is not true, because the light spectrum that you do for one sun and the light spectrum that you do for indoor are totally different. So you need to completely rework the devices. You need to innovate on the architecture. You need to innovate on the porosity of this semiconductor. You need to design molecules custom for this indoor photovoltaic applications. So this was actually one of like a very unique kind of a result that we have put it up. Then comes the second part. So we find out mass transport is one thing, you can actually address it using some methods. Then the recombination. So there are various ways by which you can actually address the recombination. One thing is that you can make molecules, as I told you, with certain functionalities like the alkyl groups or branches, which prevents the back electron transfer. So we actually came up from the electrolyte side, a very interesting, innovation where we introduced an asymmetric dual species electrolyte. So normally, the copper metal complex, it is having copper 1 and copper 2 oxidation state, and the redox potential is around 0.93 volt. What we have done is that, the recombination mainly happens with the copper 2 species. We slightly changed the molecular structure by introducing a halogen atom, by attaching a chlorine atom to the copper metal center carefully. So what change it made to the redox potential? The moment you are having a electron donating this withdrawing chlorine atom there, this redox potential moved more negative. So conventionally, like you are having 0.93 volt, but for the oxidized species, it is 0.69 volt. So what you see here in the red arrow is the recombination driving force. So conventional system, you are having this much of recombination driving force, the recombination will be very fast. But the moment you go for a smaller one, this one, there you are reducing your driving force for recombination. And that reflects in the rest of the parameters. And we went more deeper. Due to the limitation of time, I'm not going deeper into the particular study, but I request you to refer to this particular paper, and where you will get the entire details. And you can write to me in case if you are having any doubts. So it's a very interesting study that we have done. We went, it took almost like 3-4 years time to complete this work, where we went to find out the actual mechanism that is happening, and that was very tough, because you take the molecule, you add all the additives, then you let it crystallize, you make the single crystal, then you solve it out. And then we find a completely interesting kind of a dual species mechanism coming out there. And what we have observed is, normally, the copper, oxidized copper 2 complex is very unstable. So the moment you take a conventional copper 2 complex and you put it in an electrolyte, In the electrolyte, you add additive, like tertiary butylpyridine is one additive. The moment this molecule sees the tertiary butylpyridine, it just disintegrates all the ligand, and the entire TBP get attached to the copper. That's a non-phenomenon, it's non-fact. But the moment you make this chlorine coordinated system there, what we have observed is that we were able to actually make some intermediate species with less number of tertiary butylpyridine, which is attached to the copper. So how it helps? Because your electrolyte need to go to the counter electrode, isn't it? Your oxidized electrolyte, once it takes it needs to go to the counter electrode to take the electron to complete the cycle. So when you are having this kind of tertiary butyl groups which are attached to your molecule, then this actually blocks the molecule in getting closer to your counter electrode, not the photoanion, but the counter electrode. So that is actually reflected in the charge transfer measurement. We did some dummy cell measurements, and what we have seen is DMP4 is the conventional electrolyte. So with the passage of time, the charge transfer resistance on the counter electrode side increased drastically. But when it comes to the new electrolyte, it was almost the same. And then we went into the real device, where what we have done is that we use the same kind of a dye combination that Michael Gretzel used in the Nature Photonics paper in 2017. And we changed the electrolyte from the conventional electrolyte to the 5-coordinate electrolyte. And what we have seen is an improvement in performance from 28% all the way to 35%. And more importantly, we have seen this improvement under very low illumination conditions like 200 lux, 50 lux and all. And this was actually published in the same Journal of Material Chemistry at that time. Like, this was the highest reported efficiency. But again, afterwards, there were reports that came with the 37% and presently like our own report with the 40%. So this is the very recent update. So this paper is not completely out. It's still under advanced article version, where what we have done here is that one of my students, Jebin, she introduced a new triphenylamine dye. So we use the same dual species electrolyte, and along with the dual species electrolyte, this RJC6 is a co-sensitizing dye that we have developed in our group. And with that particular dye, in combination with the XY1B, we are able to make a very uniform layer of TiO2. And that helped in having a better lifetime, a lower transport time, and a higher diffusion coefficient. And finally, realizing the record efficiency of 40%. And it maintained about 35% efficiency over a range of light intensities ranging from 100 lux all the way to 6,000 lux. And this particular work was also, they selected this work as the cover page article for the Journal of Material Chemistry A. And pretty soon, like, you'll be able to see that published. And another from the engineering side. So now you have seen from the molecular side, from the semiconductor side, from the electrolyte side. So, one very interesting thing with this area of research is that it's a truly interdisciplinary area. It is not just the chemistry, physics, everything is there. Material science is there. Device engineering is there. So this is a very interesting work that Andrew has done. So conventionally, these solar cells are made with 2 holes. Why hole? Because you fill an electrolyte through these holes. So Andrew actually made some modifications into the device architecture, and he made a hole-free, spacer-free device. And bottom, you can see this is actually a module, a small module of 5 centimeter by 5 centimeter module, which is made with the same kind of an architecture. So this is very unique in a way that when it comes to commercialization, you actually is able to gain more active area there. Okay, so that is actually a better thing. And when it comes, like, I'm actually finishing up from the R&D side here. So there, initially when we started in 2015-16 time, you can see a conventional temperature sensor and a clock, which is being powered by a 5 centimeter by 5 centimeter device. Then with the kind of science which is developed in the lab, by introducing the new dyes, the new based electrolytes and all, few years back, the same system was being powered with the 2 devices which are connected in series. And again, now that development reached to a point where even with a single device, you can power these kind of gadgets. So presently we stand at a point where, like, we do have a few patents which are on the go, where we make around more than 40% kind of devices. And now the translation. you make small area device. So going from a small area device into a larger module, it involves a lot of steps. So one main part is having the right equipments in your hand, where you can translate the small device into a larger one. Okay, so this is actually done as a DST supported project in 2018, where for the first time in the country, we made a series of equipments which actually can be used for transforming the small area device into larger modules, like what you see. You can make it in any dimension, you can make it in any design, any shape and form factors. So then the point comes, like, when it comes to this solar cell, it is not just the die, the semiconductor or the electrolyte, but one of the major thing that contribute to the cost is actually the conductive substrate, the FTO substrate. So that occupies almost 80% of the cost. So if you really want to commercialize, you need to indigenize that coating. So this is where, like, we partnered with a startup company and we designed a set of equipment, spray pyrolysis based equipment, and we optimized the process where presently, like, we make conductive oxide coatings which are far better, having the sheet resistance better than even the commercial kind of conductive glass coated substrates that you are getting. And this is actually the various processes which are involved in this thing. So where you make, there's a plasma treatment there, and followed by the spray pyrolysis of these things. So in a nutshell, we have actually devised advanced R&D, indigenization of equipments, turnkey solutions, and innovative applications. So this is actually our lab. So it's one of the state-of-the-art lab in the country for the photovoltaic-based research, third generation photovoltaic-based research. And major part is on the characterization. We have actually come up with a very unique kind of electrical and optical perturbation tools optimized for studying these devices in more detail, and standard protocols for the measurements where you can do all these things. And this is not restricted to the dye-sensitized solar cell, because as you all know, like many of you may be aware, so perovskite solar cell is an offshoot of dye-sensitized solar cell. So here, instead of the dye molecules, you are using a organic-inorganic hybrid material, which is a perovskite material, with a general formula of ABX3. So A is an organic cation, B is a metal cation, and X is a halide ion. So you can actually change these metals and organic cations and the halides, and you can tune the band gap. And the most interesting thing is that these devices over a period of 10 to 12 years have gone from less than 1% efficiency all the way to 26% efficiency. So it's a very hot selling topic these days. So we also do work on this area. So we have optimized a set of fabrication equipments, and major facility has been created, and we target on three major things: not only the efficiency, but also on the stability, the cost, and the scale up. So in this regard, we made some perovskite solar cell with the carbon-based electrode. Conventionally, we use the metal deposition, the gold or silver deposited devices. But since the scale up and the cost was a major thing, like we went into the carbon-based electrodes, and there we have realized efficiencies of, let's say, like close to around 11% under the one sun. And this is a very recent thing where we have reached up to 22% for the indoor efficiency. So here you can see the same kind of a temperature sensor and a clock, which is powered by not a DSSC, but with a perovskite solar cell, which is a simple printed carbon-based perovskite solar cell. So when it comes to perovskites, these are some of the higher numbers. Presently, we are at close to 17 to 18%. So I'll just show you a small video which will brief you whatever I have shown, introduced you so far.
The global energy crisis, intensified by the pressing challenges of climate change and an ever-growing population, has necessitated a paradigm shift in our approach in how we generate and harness energy. The evolution of Industry 4.0, connecting people, machines, and systems through Internet of Things, is enabling a transformative era in the present century where battery-powered connected devices play a pivotal role in expanding our technological landscape. With 15 billion primary batteries disposed annually, we are polluting more than 0.3 million square kilometers of land. Replacing batteries, realizing self-powered devices not only reduces the carbon footprint from used batteries, but also lowers the volume of mined raw materials, thereby improving the entire value chain. Aligning with our nation's ambitious goal of attaining net zero emissions by 2070, CSIR National Institute for Interdisciplinary Science and Technology, with a decade-long experience in the area of molecular photovoltaic devices, envisions spearheading a transformation in indoor ambient light harvesting technologies. CSIR-NIISF has achieved indigenization, pioneering the development of equipments for indoor photovoltaics, alongside the establishment of standardized characterization facilities and supply chain. NIIST has successfully optimized the fabrication processes for indoor light harvesting small area devices, master plates and modules, realizing higher performance under indoor light compared to conventional solar technologies, achieving self-reliance and Atmanirbharta. Indoor photovoltaics is predicted to achieve a market of $850 million by the end of 2024. This marks the commencement of an unparalleled breakthrough within the energy sector, as we strive to cultivate an off-grid, self-sustaining power ecosystem through innovative approaches in light recycling technologies.
So, like that is actually the genesis of the entire science that is being done in the lab. So now, like, you made a technology, you have the equipments, you have the process, you made the prototypes, modules, and all. So what's next? People will not take a science just as such, it's great or like it's indigenous. It needs to be attached to an application. So we went into finding certain very unique applications. So one thing that we identified was the air quality. And when it comes to air quality, we all are worried about the outside air quality. But like the indoor air is 5 times more contaminated than the outdoor air. So many of us are not aware about it. And there, how you need to monitor? You need to have air quality monitors. So are you going to use the batteries again to power these systems? Or like, are you going to connect it to the grid? So this is actually the point where, like, we came up with a off-grid self-powered indoor air quality monitors by attaching these kind of indoor solar cells. So there we custom designed certain modules, and this is actually one of the first prototype that we have developed, where you can see a temperature and humidity monitor, and this is powered with these kind of solar cells. And again, like this was, we further partnered with a startup company called Embodied, and we reworked on the entire thing, and we came up with some very interesting kind of development. And this was tested in different real life situations, like one in Vande Bharat, and also in airports, because the movement of people inside the airport is like a very critical thing. Like post-COVID, airports are considered as one of the prone places where the diseases or the viruses and those kind of transmission happens quite a lot. So there we actually partnered with, we signed an MOU with the Thirumurugan International Airport, which is very near to us. And there actually, then the requirement all changed, because the airport authorities are not interested to put a solar cell just like that, because it is a science which is indigenously developed by some lab in the country. No, they are not interested. They wanted to be integrated with some art form. So that actually led to this particular unique development where, we made solar cell more beautiful also, more attractive. And we installed, this installation was done in last July, this 4 or 5 months back. And again, like we didn't stop there. We further improvised the system, added more artistic functionalities. And just like last month, we have this one of its kind of installation, the first of its kind of an installation, a complete full-fledged air quality monitor. And that too, like we added a science in the, like, along with the art. Communicating it with the outside world. So this is where we stand. So like the difference here is that, this is actually, if you are going through Bangalore airport, you can see this air quality monitor which is there, and this is connected to the grid, and it's very hard to see the things there. So at that same time, like you are having something here which doesn't have any batteries, which is not connected to the grid, which actually works with the light which surrounds it, and it does have a very unique kind of displays and things like that. So what we believe is that this is the beginning of an unprecedented breakthrough in the energy sector, where we are trying to actually engage our research in such a way to lead to a battery-free world through the ambient light recycling. So maybe sometime down the line, instead of these kind of button cell batteries, maybe a more sustainable solution we can come up with. So we try to do it in various sectors like building, transportation, like the urban rooftop farms and things like that. So I stop in here, and thank you all again for having this discussions. And this is actually my team. So they are the main people behind whatever I have shown to you and discussed with you today. So if you are having any queries, please do, you can write to me. And if you are coming to Thirumurugan, you can actually come to our lab, you can make a visit and all. So thank you.
Yeah, awesome, I can say. I think you may have some questions from the participants. I think already one question is there. Can we use the symmetrical system like accepted donor accepted or donor accepted donor system to make a donor cell? I think that's
Yes, I have seen that one. You can actually, the symmetric systems, like maybe like you have seen that in the previous talk where Dr. Satish might have shown you like a donor accepted donor kind of system. For polymeric solar cells, that's fine. But when it comes to dye cells, you need to have like, a binding group. You need to pull the electron out. It's a donor pi acceptor. Normally, like we prefer to have a donor pi acceptor system so that the electrons from the donating part will move towards your acceptor, and that get injected into your semiconductor. Yeah.
I think no other questions so far. I think I may add one question. Actually, you have said that you can monitor the air quality using some solar cell, right? So what kind of materials, what kind of things will be added to your system so that I can sense the air quality?
No, it's actually...
we are just powering it, right?
Yeah, we are just powering it. Like the sensors are all like commercially certified sensors. So normally, air quality monitors, either it need to be connected to a grid, or it need to have a battery or something. So there we identified air quality as a vehicle, because the thing is that indoor air is more critical than the outside air, that people are not much aware about it. So indoor air quality monitors, the moment you put an indoor air quality monitor, conventional solar cell won't work in that kind of indoor light conditions. So that is actually where, since this particular solar cell is capable of harnessing the indoor light, this is an application together with which this can be sold out. The problem is that we do a lot of science, but for any technology to be successful, the requirements are different there. It should actually reach to maximum number of people. Commercially, it should be viable. The cost. So, n number of other things are there. So that is why we work on various different products in the pipeline. So another product that presently we are working are the remote controls, self-powered remote control, so that you don't need to change the battery for remotes. So similar kind of applications are there.
I'm thinking what will happen to Duracell and all these company people.
No, we need the battery. It is not like completely eliminating battery, but at some stage, in some of these gadgets, at least some extent, if you can replace with something like this, you can reduce the carbon footprint and to a greater extent. Yeah, there is another question I am seeing it: future of organic solar cells in indoor photovoltaics. Yeah, organic solar cell actually it has taken a big leap in the last 2-3 years time, because previously the efficiencies and stability was a major issue. Now with the use of new donor acceptor, donor kind of new polymeric materials and small molecules, the efficiency has gone up to 18-19% under the one sun condition. But there, of course, I think Dr. Satish also mentioned the same thing. OPV or polymer solar cell is always prone to instability problems, because degradation is a major issue. So for indoor photovoltaics, as of now, dye cell is the best candidate, because it's very easy to make. less kind of problems associated with the stability and other issues. So yeah, so that actually kind of answered the next question also. Like we do have accelerated testing that is done on these devices. Like before it goes to the ground, these things are done. So I would say, like, 25-30 years time, nothing will happen to it. Particularly, you are keeping it in those kind of conditions where it's not a harsh condition. But who is going to keep your electronic gadgets for that much years? Like people will change everything in 2 years, 3 years these days. For example, even the remote control, like in 3 years, 4 years time, people change the television. Then automatically you go for a new remote control. But that is where, like, we are trying to build the ecosystem in such a way that you can have, like, retrofitting kind of system. So once you are changing a remote, like, you can give back and you can actually take the cells, you can refurbish and you can give it back. Similar kind of things can be done.
Okay, I think it's replied. Okay, I think they are worrying about future in the sense. So you were saying about positivity of photovoltaics. What about negativity? Like you were saying that we have a lot of junk at the batteries now. Like that, you are making a lot of molecules. So what will be the future of those molecules?
Yes, that actually, this is a very, very serious issue that we all need to think about, because we should start that from the silicon solar cells. Because 10 years back, India's total installed capacity of silicon solar cell was less than 1 gigawatt. And at the same time, presently, it is around 70 to 80 gigawatt. And in another 10 years time, we are targeting for like 400 gigawatt or 500 gigawatt. That is actually where we are trying to move. And we want to be net zero by 2047. That is the target. So imagine, with a lifetime of 25 years, 30 years, there are a lot of this electronic waste that is going to come out. So compared to that, for this kind of molecular photovoltaic devices, it can be more easily recycled. Means whatever be the molecules that you are using, you can actually take it down at the end of the product, and you can recycle and reuse it. So but still, like, being chemicals, you need to be careful with the handling and all. But compared to the conventional photovoltaic technologies, this is far better. But at the same time, I would also point one very serious concern that is there in the photovoltaic industry right now is lead, because perovskites, whatever I mentioned, so those ABX3 molecules, so those uses like the methyl ammonium lead iodide or those kind of systems which contains the lead. And this is also something that is under research presently. Maybe in a near future we can come up with something which is lead free and at the same time as efficient as a lead based system.
Okay, I think we can wind up it. I should thank you like anything, because we just moved from lab to industry very fast, and indoor photovoltaics awesome. So thank you for your valuable time.
Thank you. Thanks a lot.
Awesome presentation. Thanks a lot.
Thank you. Thanks a lot.
I think we're talking it.
Okay, bye.
I know.
We have come to the end of today's session. I thank both the speakers for this wonderful session. Tomorrow, I request all participants to please put your attendance in the link provided. And tomorrow we'll be again meeting at 6 p.m. today. Thank you again, sir. Thank you, everyone.
Thank you. Thanks a lot. Yeah, bye.
Thank you, Dr. Suresh. Thank you.